what their methodology was, but they were saying that 73% or 70-something% of adolescents going back to school have had at least one dose.
Mm-hmm.
Yeah.
So I think it's almost time already, but and we don't have our chairwoman, sorry. So well, we can wait maybe one more minute because I see people joining.
Who's the chair, in fact? Because
Sophie, but she may not have understood it from the program
because it's not repeated.
Yeah, but she's continuing the session from yesterday. That's why.
It's just continuing the session because it's about upcoming surveys, and we're now going to splashback radii.
Yes, okay.
It was not obvious. Poor Sophie. I don't think she could have guessed she was the chairperson.
So, Lindsay, you can do it?
Yeah. Shall we make a start?
Yes, I think let's go. Otherwise, it's 32 now.
Okay. So welcome everyone to the last day of the meeting. We're continuing on with our theme of galaxy cluster detection and mass estimation in the context of upcoming surveys. And the first talk we have is by Anthony Gonzalez from the University of Florida on splashback radii for individual clusters. So take it away, Anthony, and I'll give you a 3-minute warning.
Okay, that sounds great. So first, thank you to Lindsay and all the organizers for putting together a very enjoyable set of talks over the last few days. I am taking things in a little bit different direction from where we left off yesterday, with kind of a forward-looking talk, thinking about what we can do in terms of measuring splashback radii for individual clusters. So I'll start a bit generally, and then I'll talk about work that I've done with my collaborators that are shown here in green, and a bit of upcoming work that also includes the folks shown here in blue. So we're going to hear more about splashback radii later in the sessions today, and we've heard a little bit up to this point, but just to get everyone on the same page, all the splashback radius is it's a maximum radius that any infalling material into a cluster halo reaches after first core passage. So if you look in the central figure here from Benedict Diemer, you end up with a very distinct boundary, which is that apicenter of the radius. And it was realized by Diemer and Kraftsov and Adhikari in 2014 that this is a physically observable, well-motivated feature. And it shows up as this kink in the density distribution. So if you look on the right-hand side, you can see how the density distribution flattens out. Beyond that, you're only seeing the material that's infalling for the first time. Inside of that, you're seeing the material as well that's orbiting in potential. And if you look at the logarithmic derivative of the gradient, or the logarithmic gradient of the density distribution, you see this very steep feature. And it's the minimum of this feature that corresponds to the splashback radius. Now, to first order, this is going to be depending on the halo mass, and the scale is going to be very similar to R200. But unlike R200, it's something that, as an observer, one can go out and measure, which is reassuring. And to second order, it's also going to be dependent on the accretion history, in the sense that for things that have more recent accretion, the splashback radius, the ratio of the splashback radius to R200 will decrease. So you can use that ratio to try to get a sense of the accretion history. All right, so subsequent to the 2014 theoretical work, there's been a great deal of observational work focused on stacked analyses. And as you can see, this has been done both with looking at galaxy density distribution and looking with weak lensing shear by a number of different groups using a number of different cluster catalogs. And I think it's really been impressive, the progress that's been made just in that 7 years. And just as an example here on the right-hand side, this is a figure from Shin et al. 2021, showing for the ACT-DR5 a comparison of what you get from weak lensing shear and what you get from galaxies. And you can see that both approaches give very consistent measures of the splashback radius for this sample, showing that they're unbiased relative to one another. Now, what I'd like to make the case for right now is that what you really want to be doing, if you can, is moving the next step and trying to be able to do this for individual systems. We've heard discussions over the last few days in different contexts about the pros and cons of stacked analyses versus individual measurements. And here I would say that the argument for individual measurements comes down to two key things in my mind. The first is that there's a nice paper from last year by Benedict Diemer showing that if you measure masses within the splashback radius, you have a more universal mass function, particularly at redshifts less than 2, than you would get from M500 or M200. And you can really most cleanly see this by looking at the bottom of the figure, where this is the ratio of the mass function at different redshifts to redshift of 0. And you can see for M500, there's a very large change as you go through redshift, and for the splashback mass, it's minimized, these differences. And so this argues that if you can really calibrate your masses into measuring within the splashback radius, that reduces the variation you have to deal with for cosmological purposes. In addition, as I noted before, the ratio of the splashback radius to R200 is a probe of recent accretion. This isn't the only probe of recent accretion that we have for clusters, obviously, but the timescales are going to be different for this versus something like the X-ray morphology. And so it's added information that you can use if you have R200 masses from any of the different mass measures that we've been talking about. And so there are both astrophysical and cosmological reasons for trying to get individual splashback radii. Now, the catch on this, obviously, is that you have to have a tracer that has sufficiently high signal to noise that you're able to trace the mass distribution all the way out to the splashback radius. In this mass measure, or this measure has to be unbiased relative to the total mass distribution. And you need to be able to do this for enough systems that you can calibrate whatever your mass proxy is or within the splashback radius, or directly measure masses within the splashback radius for that sample. And so I think there's a lot to be gained by pushing on this regime for the galaxy density distributions and the lensing for the most massive systems. But I'm going to go a little bit different way with this talk and focus on something that I think is arguably novel, if challenging. And particularly, there was a paper earlier this year by Elise Deason where she used the Sea Eagle simulations. And she was asking the question of how will the stellar distribution trace the overall mass distribution? And what she found was that if you look for the caustic corresponding to the splashback radius with the stars, it's unbiased relative to the dark matter distribution. And the profile that's shown here is just the median at every radius, which so includes the galaxies. But she also made the same plot with the galaxies excluded, and you even get a little bit deeper minima, which is also unbiased. So she argued in her paper that the intracluster light should provide an unbiased tracer to detect the splashback radius. Now, you should be looking at this at the moment with a healthy dose of skepticism. Even if you look at the stacked analyses from DES, work by Zhang et al. And Sampaio Santos in the last few years, those analyses reach out to about a megaparsec. So we're now talking about going out to multiple megaparsecs to measure a feature using a tracer that hasn't gone out that far before. But what I hope I'll convince you is that this isn't as crazy as it seems. And even before this paper, our group was trying to take a look at one of the Hubble frontier field clusters in preparation for upcoming space surveys to ask the question of how far out can you really feasibly try to probe the intercluster light. And initially, we were hoping that we'd be able to get around a megaparsec and then be limited by systematics. It turns out we can do a bit better than that. The particular cluster we chose was MaxJ 1149. It's the most distant of the frontier field clusters, so you get out further in physical radius, and it's also a merging system, and that'll become important in a little while. So we're certainly not the first people to look at intercluster light in the frontier field clusters, but really the Achilles heel of Hubble for this type of work is that you can only get out at the redshifts of a half that we're looking at here to radii of about 400 kiloparsecs. At these radii, you're still dominated by intracluster light, so background subtraction is a problem, and it also means obviously we're not going to be able to get further out with just the frontier field data. So what we did is we took the primary and the parallel fields for this system, and we had a geo program that linked up, just bridged with short observations, 6 orbits, the primary and the parallel WIF C3 IR data to give us continuous coverage going all the way from the center out to about 2.8 megaparsecs from the cluster center. This is the schematic of what we were doing. The exact field that we ended up with is shown in the red here. I'm also overlaying for completeness the merger axis here. The weak lensing centers with the green symbols here. And you can see that we're centered, for the BCG ICL analysis, and we talked about, we're centering on the BCG in the major subcluster here. So we have one angle going out from this system. Again, we go out to about 2.8 megaparsecs, and we use the region beyond 2.4 megaparsecs to measure sky. I'm happy to answer questions about how one deals with all the systematics like persistence, masking, sky variations afterwards, but for now, I'll just say that we spent a great deal of time on the systematics. So once you do this, you can create a radial profile going out along the axis that we have probed here. And this is the surface brightness profile that you get. And I'll point out a few things here. So first, we've also included the DES composite 2019 go in the R band. Because we're in the infrared, we have a better signal just because we're moving towards the peak of the stellar emission. Second, you see a very consistent profile in both of the filters. And third, I'll highlight, you see a couple different kinks in the distribution, so inflection points. You see one here that's a bit under 100 kiloparsecs out. You see another one here between 1 and 2 megaparsecs. And this is more clearly seen if we look at the logarithmic gradient. So the first of these is the transition between the BCG and the ICL, and this is also seen in the DES stack there. And the second is the caustic and the density is what we interpret as being the splashback radius. You see it in both filters with the blue line and the red line, and then the weighted composite of those is the black with the error bars. If you compare this with the simulated clusters from Sea Eagle, the orange is an ensemble average, which has a minimum right about the splashback radius. The other two are major mergers that have moved in. And then the black is ours. And you see the shape and the depth are comparable with what you'd expect. The only difference is that we're shifted in a bit. And there are a couple different possible contributing factors that I can talk about later as well. But the key thing I want you to take away here is that the functional form is similar. So it looks like we really are getting the splashback radius. If you only take two things from this, the first is that we're getting out to multiple megaparsecs measuring the ICL with HST, which I think is very promising for upcoming space-based missions. And at least for this system, we seem to be able to detect the splashback radius. Now we'd like to move forward finding it in more systems and seeing how well we can do. And so we have a cycle 29 geo programming coming up for the rest of the frontier field clusters. Here we're going to be able to build on upon the Buffalo survey data, which is wider field than the frontier field data itself. So we only have 2 pointings necessary between each of these, and we'll be able to do these other 5 systems as that data comes down. I don't expect us to detect splashback radii for all of them, but particularly for the mergers and the less massive ones, I think the prospects are quite good. And so finally, that's, I guess I should say, with this data, we'll also be looking at the 2D correspondence between ICL and dark matter, and I'm looking forward to the next talk on that topic in a minute. And looking further forward, I think the key thing to keep in mind down the road is the field of view of WIFC3I is 160 by 160 arc seconds, so 10 to the minus 3 square degrees of order. With Roman and Euclid, we're going to have 1/3 to 1/2 square degree per pointing, which really helps with the systematics. We no longer have to stitch data together. And the depth is plenty sufficient except at the highest redshifts. So really, this is all going to be about systematics. And I know at least on the Euclid side, the low surface brightness group has been putting in a good bit of effort on understanding and controlling things like scattered light and thinking about galactic cirrus. So I'll end there and just say I'm looking forward to trying to add one more tool in the toolbox for cluster mass work.
Great. Thank you very much for that really interesting talk. If anyone has any questions, oh, yeah, we've got a lot of questions. Okay. I'm going to ask first Shantanu.
Yeah, so just a clarification or a semantics related question. So is the concept of splashback same as the concept of caustics, which your colleague P.S. Sikvi has been arguing for more than 2 decades? I think he's been arguing for ring caustics, if I recollect, and only in the Milky Way.
That who has been arguing? I missed the word.
P.S. Sikvi.
Yes. So Yes, he's focused on density caustics due to axions and having matter treated as a Bose-Einstein condensate. Here, we're just talking about density caustics due to infall. So they're both caustics. They're a bit different in context.
Thank you. But the shape is the same, or?
No.
Okay.
The shape is going to be different.
We have 5 hands up, so I'm going to go really quickly now. Andrea.
Oh, thanks. Very nice work, Anthony. I just want to mention, okay, this is establishing the splashback using photometry, basically. We were trying with Barbara Sartoris to use the Clash VLT sample to use actually redshifts and the caustic technique, Diaferio, Geller, and Rines to get, in fact, the mass density profile directly. And it's pretty tough, but we are working on that. Who knows, maybe we get to some result. My question is, suppose I want to use galaxies. So the number density profile of galaxies to detect the splashback. Should I be using all the galaxies? Should I be selecting the red sequence galaxies to be less affected by background? What do you think?
I don't think you want to restrict yourself to the red sequence galaxies, because you want to be able to include things. I mean, so it's true that if you select red sequence galaxies, you're going to get rid of a good bit of the infalling material. But I think you're going to decrease your signal to noise as well, because you're going to lose a lot of things that have infallen, but just they're out towards the splashback radius and have not yet been quenched. So the analysis I was showing from Elise Deason's simulations, she was just using everything.
Okay, so next was Gary.
Fantastic work, Anthony. Congratulations. So you're doing the ICL, so you're throwing out the galaxies, or you're summing up everything? That's my first question.
Throwing out the galaxies.
Good. And then my second question is, how can you get, well, you said that your backsplash radius was, well, you showed a plot that showed that it was about 0.6 R200. Was that R200 critical or R200 mean?
Oh,
So if it's R200 critical, how could you get a backsplash radius that's smaller than the viewer radius?
right. I think it's, oh, I forget details from my own paper sometimes. I'm pretty sure it's mean.
Okay, so that would be better.
Yeah. Now, it is smaller than I would have expected. I wouldn't have expected anything less than 0.7 R200 regardless. And this may partially be a function of the fact that we only have one direction going out, so we're getting affected by the ellipticity of the system. And a first order estimate argues we shouldn't be down there, but it's hard to say until we get full azimuthal coverage. And that's one case where things like Euclid and Roman are going to make a huge difference.
And then for the historical record, with Trevisan in 2017, we stacked the density profiles from Sloan using the nearest cluster to every galaxy. We went out to 20 real radii. And we did talk about features of backsplash radii that we see in both the SDSS and in simulations. They were not exactly the same radius, but otherwise everything matched.
Yeah, for historical completeness, I should also note that the idea of splashback radius certainly didn't come out of the blue in 2014. All the Goldreich and Fillmore and Bertschinger papers back in the 80s really
Exactly.
laid the groundwork.
It used to be called backsplash until Benedict came around.
Right.
He's been very persuasive.
Yes.
Next, Yuanyuan.
Yes, thank you. So Anthony, this is really nice. Thank you so much for this talk. I was wondering, like, when you look at the inflection point, have you tried measuring splashback from like the cluster galaxy distributions or something else and see if they're consistent?
I have not. I don't think that we would have the statistics for this system to measure it from the galaxy distribution. Again, it's only a single system as opposed, and so we can't do something like the stacking analysis that's standard right now. And we only have that one angle, so we're limited in multiple ways in terms of our statistics. What we can do as the lensing models advance here, try to compare more directly with the dark matter distribution.
Okay, so final quick question from Matteo, and then we'll have to move on.
Hi, Matteo.
Just two brief questions. When your detection is right at the edge of your field, question number one, and question number two, how do you remove the galaxies?
No, it's not right at the edge of the field. Let me go back, and maybe I can point on here. It ends up being right about here, if you can see my cursor. So it's well into the bridging fields in the middle. The outer parts of the field are really just for background subtraction. And the removal of the galaxies, basically, we end up doing, or I end up masking and then growing the masks and checking for robustness so that the answer is not changing depending on, as you grow it anymore. Okay. Is that what you were asking, or do you have
it's not model subtraction. You make a whole.
No, I don't trust models for things like this.
Okay.
And then the profiles are median profiles. So if there's any individual thing that's giving a residual, that gets washed as well.
Okay, thanks.
Sure.
Nice.
Thanks. So thanks again, Anthony. That was really interesting. And next we have Yuanyuan Zhang, who's going to be talking about something similar. Is there a relation between intracluster light and galaxy cluster mass? So if you can share your screen.
Is everything working?
Yes, it's in full screen now. Perfect.
Okay, great. Thank you. So intracluster light, as Anthony has talked about, refers to this diffuse low surface brightness permitted light around the massive galaxies and really throughout the cluster space. And in this optical image from the dark energy survey here, if you have a really good monitor and really good eyes, you might be able to spot it a bit in between the two massive galaxies here. But as Anthony and many people, including myself, have shown, intracluster light really extends to a much larger distance and can take up a big fraction of the galaxy cluster stellar light. So today I'm going to try to answer the question, is there a relation between intracluster light and galaxy cluster mass? So back a few years ago, when I was a young graduate student, I was told that when you present a question as a title of the presentation, most probably the answer is going to be a no. But I'm going to break away that tradition and argue for an answer that is most probably yes. So this talk is going to be based on two published papers, then 2019, and also a paper by my graduate student collaborator, who is now a proud teacher at Brazil Navy Academy. So I also want to acknowledge that this is a very much active field with a lot of enthusiastic people working on this with a lot of great expertise. And in fact, just about 2 days ago, there was this wonderful paper by Huang that is very much relevant to what I'm talking about here. And throughout this conference, we have also heard people talking about this topic, including Jesse Goldie-Marks and Riccardo Seppi talking about the relationship between ICL and galaxy cluster mass measurements. And of course, the wonderful talk that has just been given by Anthony. So I will be focusing on my own analysis with my collaborators. For our study, we try to look at the average properties of intracluster light in the dark energy survey data. For this method, we have hundreds to thousands of galaxy clusters now, really. We would look at their images and then pick out the center galaxies in these galaxy clusters, and then try to measure the surface brightness of the BCGs and intracluster light as a function of cluster radius here, as shown by the individual black lines in this plot. And then to improve the signal to noise of the measurements and also to deal with a lot of different systematic effects, we would average the profiles and subtract contaminations and backgrounds and derive the averaged profiles for these hundreds or even thousands of clusters to come. So once we have these kind of averaged profiles, we could split the clusters into according to their different properties. And the first thing we did is that we tried to see the mass dependence of the intracluster light profiles. So here, this plot is showing like the surface brightness of galaxy clusters. of intracluster light and BCGs as a function of their distance from the cluster center. These 3 lines is for clusters of 3 different richness ranges and therefore 3 different mass ranges. The black line here is the most massive clusters, and blue dotted line there is the lowest mass clusters. So by no surprise, we saw that, you know, more richer and therefore more massive clusters have more intra-cluster light in it, and lower clusters of lower richnesses and less massive clusters has less intra-cluster light. So another interesting thing that we saw is that once we scale this surface brightness radial measurements by the cluster radius R200, we saw that the profiles become quite similar there. So, you know, it's like at large radius, it kind of like is consistent within their error bar. So I call that self-similarity, but it's really a rather cheap definition of self-similarity according to like, you know, compared to what other people would use. But bear with me. So it seems that the profiles are quite similar once you scale them by the cluster radius. So that really makes us think that there is probably more, something more that is to the relation between intracluster light and galaxy cluster mass. As with this question, is there a relation between intracluster light and galaxy cluster mass? If we look into this question, I think, you know, you could further break that down into 3 questions, or at least we try to break that down into 3 questions. The first question is there a scaling relation between intracluster light luminosity and galaxy cluster mass? We think that more massive clusters has more intracluster light. So the answer here is, we think is yes. Although I would also warn everyone here that this is still an unsettled question, and there is, this is still being studied. And then the second question is, if there is going to be this scaling relation, what is this scaling relation like? Is it a power law? Is it a good relation? Is this power law relation has a low scatter? So that's what I'm going to try to answer next. So we looked at the intracluster light and BCG luminosity as a function of cluster richness, which is the mass indicator we have. And we integrated the intracluster light luminosities in different apertures here. The green ones here is the intracluster light integrated to the largest apertures, and the red one here is integrated to the lowest apertures. So what we found is that, you know, when we look at the intracluster light luminosities inside galaxy clusters, especially at a rather large aperture, there is a quite linear relation between the log values of cluster richness and intracluster light luminosity, and the slope of those power law linear log relations is quite significant for intracluster light. So this tells us that, you know, there is some sort of traditional relation, power law relation between this scaling relation. And what is more interesting is that when we compare this kind of relations to the relations of cluster total light, we find that the intracluster light profile is quite steep, at least as steep as that of the cluster total light. And when we look at the correlation coefficient of these luminosities and cluster richnesses, it's also quite significant. So here we want to argue that, you know, there is a good relation, there is a power law relation, and it could potentially be a rather steep relation, actually. And, you know, we could further get more information from the intracluster light properties in simulations. So here we looked at the data from Illustration J301, the hydrodynamic simulation, and we looked at the diffuse stellar content integrated with different cluster aperture radiuses here. So the upper panels are the stellar masses of these ICL stellar masses as a function of galaxy cluster masses. So what you want to look at is these orange points here. And what we find is that there is a linear log relation there, and it's especially steep at large apertures, just like what we found in the observational data. And the next thing we want to look at is the scatter of this power law relation. So this is what is shown on the lower panels here. The scatters of this intracluster light is shown as the orange line here in this lower panels. And what we want to compare to is the scatters of these relations of the stellar masses of subhalos, as shown as the blue lines here, and the scatters between the gas mass and galaxy cluster mass, as shown as the red lines here. So what we found is that intracluster light stellar mass relation scatter is not as good as that of gas mass, but it's better than the subhalo stellar mass. So yeah, so basically we're not able to outrun like gas mass estimates of galaxy cluster mass, but it's really good.
3 minutes.
Oh yeah, thank you. So as with how good this scaling relationship is, so our analysis thinks that it's promisingly good. And then the next question is, why is this scaling? Why is there this scaling relationship? What is this intracluster light distribution look like inside galaxy clusters? And in the extreme cases, can intracluster light help us measure the spatial distribution of galaxy cluster mass? Like, if we fit in FW profiles to intracluster light and to weak lensing measured galaxy cluster masses, are we going to get the same concentration parameters? That will be really valuable. So we further try to compare the intracluster light surface brightness to the weak lensing derived surface mass densities of galaxy clusters. So this plot here shows the ratios between intracluster light surface brightness densities and the surface mass densities derived from weak lensing for galaxy cluster masses. So we find that the ratios is not flat in the middle of 100 kiloparsec, which is not surprising because there is the BCG here. But outside of 100 kiloparsec to about 1 megparsec, this ratio is rather flat. So I'm going to skip the next a few slides here, but we did also look at profile weak lensing measurements without depending on parametric models, and found that the profiles also look pretty similar there. But another thing that, counterpoint actually came from analysis of illustrious Qingyang simulations, that we actually found that in the simulations, intracluster light is more concentrated than the galaxy cluster mass distribution. So it is not following the same spatial distributions there. So as a conclusion, basically, we right now really don't have a strong evidence answer about the spatial distribution of intracluster light, and we don't know whether or not we could actually use intracluster light radio distributions to help us measure galaxy cluster masses in weak lensing. But we do think that for all of the things we see here, we think there is a scaling relation between intracluster light luminosity and galaxy cluster mass. And this seems to be a really good scaling relation when we look at their properties in both observations and simulations. So if there is going to be one message from my talk, that message would be when in the future, when we consider measuring galaxy cluster masses, please also consider using intracluster light for this kind of work. So that's all. Thank you.
Thank you, Yuanyuan, for that really interesting talk, and we're right on time. So if anyone has any questions, please raise your hand. So first question from Chun Hao. We can't hear you, just in case you're muted.
Sorry, can you hear me now?
Yeah.
Cool. Hi, Yuanyuan, very nice talk. I'm just wondering, like, whether the miscentering will affect this ICL as a mesh tracer. That's the first question, and the second question is whether it's possible to use to detect like ICL for individual cluster and use that to help the miscentering quantification.
Yes. So For the miscentering situation there, so intracluster light, right now we define that as the, a measure that from the central galaxies, which is the same centers that we use, for example, for weak lensing measurements, all of those mass distribution measures. So miscentering would affect them to the same degree. So I'm not too worried about that because it affects everything at the same time. And as with whether or not miscentering could help us eliminate the miscentering effect. So we didn't do a quantitative analysis, but based on my experience of looking at the images, you do see much less intracluster light, like around these miscentered clusters. So I would really advocate for considering using that information to improve the centering situation of galaxy clusters.
Very true. Thanks.
Yeah.
Next, a question from Anthony.
I was just curious whether you had a teaser for what you have planned next. It's been a really nice work you've been doing. I'm just curious what you're doing as the next step.
Yeah, so we've been having a few thousands of galaxy clusters from Red Mapper. So we've been trying to measure really these things to higher redshifts. And of course, at higher redshifts, things is supposed to get better, but there's also some additional challenges. So that's what I've been working on. And I also really hope to not just to work on Red Mapper clusters, but do some multi-wavelength cluster analysis to really get a bit more information out of this topic. So thank you for asking.
Thanks.
Nice. A question from Wonky.
Thank you for a great talk. I have a naive question on the geometry. As I remember in the earlier meeting, we had some discussion of how the geometry, the ellipticity of the halo can change the weak lensing mass map. And as ICL can trace the dark halos, will that bias the aperture luminosity that you showed in the second topic?
Yes. That is a good question. So I think, this ellipticities affect a lot of the cluster mass estimates, as we've heard during these conferences. So I think that is also the same problem for intracluster light here. The good question is that, because we know that intracluster light also traces galaxy cluster ellipticities there. So everything, I think, seems to be affected to the same degrees there. Does that answer the question?
Okay, yes, thank you.
Great, thank you. Thank you again, Yuanyuan. We'll end this session there. So thanks again to those speakers. And now we're going to move to our final poster session before we go to our final theme on simulations. So Riccardo is going to chair this session for us. So I'll hand over to you, Riccardo.
Okay, thank you, Lindsay. Let me share my screen so you can see the posters. Okay, you should be seeing it right now. Can you see them?
Yeah, not in full screen, but yeah.
Not full screen. So let me. Is it better now?
It's a little bit better, but it's not fully full screen. Is there a way to make it sort of?
Let me try again. Better?
Same as before. Is there a full screen option in the?
Sure. Yeah. What about now?
Yeah.
It's a little bit too big, I guess.
Yeah, no, that's great. Oh, I see.
Yeah. Okay. I think if you can see the full. Sorry. The.
Do view full screen in PDF?
Yes. Sorry for this.
No worries.
What about now? Can you see the full poster?
Yeah, It looks
That's good. That's good. So thank you very much. Welcome to this flash poster session. So we can start with this first one from David. Sorry. From David Barnes from MIT. So sorry, Stephanie O'Neill. No, I was reading the second author. Sorry. So please, if you can start now.
Could we be doing this, the postings or the slides that we submitted?
Yeah. Good question. We just realized. Yeah, this is the poster, not the poster slide.
Oh, this is what I got. I don't have the poster slide. Maybe you have it ready, or?
No, I thought I saw it show up on a different, on someone's screen, the slide, like the mini slides. Yeah.
Okay, maybe I can. Okay, is that it?
Shall I stop sharing, Bruno? And
yeah, maybe. I don't know why. Yes, you don't have the same version. That's sorry for that.
Okay.
Okay. Yeah. So I can just, yeah. So I'm Stephanie from MIT. I'm a grad student at MIT, and so I was just looking at this idea of the splashback radius that we just heard about, using the point of steepest slope and density profiles of halos to determine halo size, and then looking at this in different components. So a lot of work with splash, like a lot of our understanding comes from N-body simulations. And then in the past several years, there's been a lot of detections in galaxy surveys and things. And so I wanted to look in hydro simulations. So I looked in illustrious TMG to see if, first off, if anything funny happened to our understanding when you threw baryons in, and not much changes there. So that's good. And then also, how your measurements are impacted if you're looking at galaxies compared to the dark matter. So if you're looking at the galaxy profiles of the dark matter profile. And then I also looked at gas, even though the physics is a little bit different, because there's a similar feature that happens there at a slightly smaller radius, to see if we could maybe correlate that and make measurements of the underlying dark matter distribution. So.
I will use it around. Riccardo?
Yeah, okay. Yes, please.
Well, hi everyone. I'm David Valles from University of Valencia. And the work I'm presenting here, done together with Susana Planedes and Vicent Kilis, in this work, we take a close look at the characterization of the accretion processes on two galaxy clusters. Since the accretion of matter and in particular gas shapes many of the observable properties of the ICM, having a precise description of such processes is crucial in order to understand many phenomena, such as the generation of turbulence, which then is linked to, for example, hydrostatic mass balance and so on. So in our contribution, we use high-resolution cosmological simulation to introduce some novel ways to characterize the nature of these mass accretion flows, both temporally and spatially or angularly. And well, on the right you have just an example of this latter. So I invite you to take a look to the poster and also to the paper we published a few months ago on this topic. So thank you very much.
Thanks to you, David. Bruno, if you can show the next one, please.
Hi, hello everyone. I'm Yuanyuan Zhang, a postdoc at the University of Chicago. Here, my postdoc presents our recent work on how mergers and smooth accretion shape the cluster outskirts. And here I want to highlight one of our interesting results, the relation between mass accretion rates and boundaries of galaxy clusters. And we all know that the evolution of dark matter halo, say the boundary of, say the splashback radius depends on the total mass accretion rate of the system, contributed by both accretion and by both accretion and mergers. And this is not surprising because total mass accretion rate reflects the deepening of the gravitational potential. But interestingly, the behavior of gas component of galaxy clusters is very different. Boundary of the intercluster medium is marked by the radius of the external strong shock front, whose evolution depends on the local smooth mass accretion rate, characterizing the strength of smooth accretion much smaller than the total mass accretion rate. And such a difference explains why there is a prominent radius offset between boundaries of dark matter and the intercluster medium. Please check our paper if you are interested in more details. Thank you.
Thank you to you. Please, Bruno, if you can show next one.
Hi, my name is Ismail, and I'm a PhD physics student at the University of Michigan. And my project is connecting the properties of dark matter halos with their growth. So specifically, we're interested in understanding what aspects of a dark matter halo accretion history most significantly impact its present-day halo properties, like concentration ratio, XF, viral ratio, etc. And we're using a rockstar catalog from the Bolshoi simulation as well as merger tree information. And we're trying to build prediction models that go from the accretion history to the halo properties to understand that relationship better. And on the right, I'm showing a figure, which is the correlation of the mass accretion history at different snapshots from the simulation with different present-day halo properties. And one takeaway from this figure is that different timescales are more predictive of different halo properties. And we can use that to leverage that to build better prediction models. Thanks.
Okay, thank you, Ismael. If you can, Bruno, please show next one.
Hello, I'm Il-Sang Yun. I'm a staff scientist in National Radio Astronomy Observatory. So in this work, I'm going to introduce a simple isothermal sphere model to model the dynamics of galaxies in a cluster. So from the wide field multiband photometric surveys, we will have many observations like this, as seen on the plot on the left, which is the galaxy surface number density profiles of coma clusters. Previously, it has been modeled by a truncated isothermal sphere, as shown in the black solid line using the King model with the W parameters of 8.5. But the system is not a tidally truncated system, and indeed is the self-gravitating system embedded in the deep gravitational potential well from the dark matter halo. So I'm going to introduce the isothermal sphere model bounded by the deep gravitational potential well, and will demonstrate that potential well can be the boundary condition with the high temperature, so the causing the embedded system in a thermal equilibrium with a large velocity dispersion, and also show how we can use this model to describe the galaxy number density profiles and also infer the properties of the dark matter halo potential well of a galaxy cluster, including the cluster mass. So for more details, please stop by my poster. Thank you.
Thank you very much, Sang. So next one, please.
Okay. Hi, my name is Ana Carolina, and I am a master's student of the University of Brasília, Brazil. Today, I'll be talking about how I plotted these two graphs using the NC Halo Density Profile class from Cosmos. First, I defined the Halo Density Profile. In this case, I used the Navarro-Franken-White profile. Then I defined some clusters parameters like the mass, the concentration, the redshift, and the distance to the center of the cluster. With these terms, it was possible to calculate the surface mass density on the left and the excess surface density on the right. So I made a comparison with the surface mass density calculation tools present in the Colossus library, where it was possible to observe a precision of the order of 10 to minus 13. That indicates a good accuracy between these two libraries. Okay, thank you.
Thank you very much.
Hi, I'm Cynthia from Universidade Estadual de Londrina. NumCosmo and CCL are cosmological libraries that have implemented the multiplicity functions, cosmological models, distance, and a variety of statistical tools. The languages used in these libraries are mainly in C and Python. Besides implementing UMS function when available, it's important the desktop. Verifying their functioning precision and execution time and the agreement level with other cosmological libraries. In our work for this task, we mainly use the Jupyter Notebook. In both figures, we bring up some of these tests, the mass function compute using Nu Cosmo and CCL, and their relative difference. Thank you.
Thank you, Cynthia.
Hi, my name is Ormila Chedemuri. I'm a postdoc at the Chandra X-ray Center at the Smithsonian Observatory. So what I would like to talk about is a paper where I used a large suite of idealized simulations to reconstruct the history of emerging clusters. So in this case, it was Able 2146, for which we had really deep observations in the X-ray, as well as in other wavelengths. So we had lensing information, spectra of the galaxies, and also low resolution SZ measurements. So there was an existing discrepancy in the literature between the masses that were predicted from almost every other metric on the one hand and weak lensing on the other. And this is a little concerning because we think of lensing as the most unbiased estimator. And essentially in my investigations, I found out that the issue here was that the prior assumed for the lensing was motivated by what we know about relaxed halos. And this really doesn't work for merging clusters. So systematically, you expect merging clusters to temporarily have higher dark matter concentrations because of gravitational compression. So I essentially present in this paper an extensive parameter study of how different parameters of the precursors of the merger affect what you see when things are really head-on. So this tool is also available to model any other merging clusters that you may have on hand and are interested in. So please check out the poster. There's also a link to this paper on the archive. Thank you.
Thank you to you, Mila.
Great, so that brings us to the end of our final Poster Flash talk. So thank you to all the Poster Flash talk presenters. Now we have the dedicated poster session. So head over to Gather Town. I'll put the link in the chat, but the link is also on Slack and in the email Bruno sent. And from that, we'll go into the break. So just enjoy the posters and make sure you're back at 5:20 local time, Madrid time. Don't know what time zone that is for all of you, but yeah, see you over in Gather Town.
See you in the spiritual world. Okay.
Okay. Bye. Bye-bye.
Hi, Lucy.
Hello.
Hi, do you hear me now?
Yeah.
Okay.
How are you doing?
So I solved the problems that I had yesterday.
Yeah, that's good.
Great. Can I just briefly share my screen just to see
Sure.
whether everything works okay?
Yeah.
Yes, I think you can directly. Or I stop sharing.
Yeah, thank you. Okay. Okay.
Yeah.
It seems that it's working now.
Yeah, we can see that.
Great. Wonderful.
Very good.
I've used a lot of those, what do you call them? Little movies in presentations. They're really nice for talking about structure formation. The ones from Multidog.
Let's see. Okay, and we stop sharing now.
Not a long time.
Hi, can I try to see if I'm able to pull up the slide and go through the slides? It's Elena speaking. So,
yeah, Elena, you can. It's
hello.
Barbara.
Yeah, there is someone already sharing the screen. I don't know if.
I think it's Bruno.
Yeah.
Maybe this video you have the power to.
Okay. To shut him. Okay. So here you see, let me see. If I do that, do you see full screen?
Yeah.
Yes.
Okay. Thank you. Stop share. Thank you.
let's give it maybe another minute while everyone comes back from the poster rooms. I was trying to see if I could broadcast in GatherTown, but I've never tried that before and I don't know if I can.
Broadcast in GatherTown.
Yeah, just like send a message to everyone to say, stop reading the posters.
No clue.
I'm gonna see if there's anything I can do.
You can, if you can find like there's like a little microphone where you can broadcast to everyone. It's like a thing you can add to the GatherTown rooms.
Do you, by any chance, do you remember where, was it like, is that on your icon?
No, I think you have to have like built, if the person who set it up didn't include one, I think you have to have host permissions to do it. But you can chat to everyone too, usually.
Okay.
Can I start sharing my screen, Lindsay?
Yeah, go for it.
Go ahead.
Camilla, I think we could make a start. I think most people are back from GatherTown. Oh, I don't hear you.
Hello?
Can you hear me now?
Yeah.
Oh, okay, good. Sorry, I always have a weird thing. I did want to check if signaling for the 3-minute mark works with Signal. Gustavo, do you see that, or does it not pop up?
No, I don't. Sorry, I don't see that because I only have Lindsay on my screen.
Okay. I'll just give a verbal cue then.
Yeah, just give me a warning. Yeah, just shout, simply.
Okay, sounds great. All right, so hi everyone. Welcome to the final session of this wonderful meeting. We are now on theme 3, a view from galaxy cluster simulations. We have 5 talks for this session that are 12 plus 3 minutes each. So to the speakers, as I was mentioning, I was planning to give a sign with an emoticon, but that won't work. So I will just verbally cue 3 minutes left and 1 minute left. And to folks for the Q&A, as a reminder, please use the raise hand feature during the Q&A. And if you would like to post a question in the chat, I'm happy to read those aloud for the speaker to then answer. All right, so first up, we have Gustavo Yepes, who will tell us about the 300 project. Take it away.
Okay, thank you very much. Do you hear me well? Yeah? Okay, so so let me first thank the organizers to give me the opportunity to talk about the 300 project, which is an international collaboration of many people scattered around the world with the common interest of producing and exploiting a large database of hydrodynamical simulations of galaxy clusters. Now, I don't want to remind you the importance of galaxy clusters, of course, because they are at the crossroad of cosmology and astrophysics. On one hand, cosmology is very important for cosmology. Galaxy clusters are very important because they are the wonderful probe to constrain the cosmological parameter once we are able to count them by mass. On the other hand, they constitute one of the best astrophysical laboratories, at least the largest ones, because they are the largest objects in which we can study the very interesting processes occurring within a deep gravitational potential of the baryons in different forms. So from the intercluster medium, the stars in galaxies, and the intracluster light, all the feedback effects occurring between stars and the gas, and as well as the supermassive black hole formation and their feedbacks and the AGN during the AGN phase. So of course, in both fields they need each other. So mostly if we want to, in cosmology, we want to know the mass of the clusters, but then on the other hand, we only know the observables, which are hard, directly related with the astrophysics of the system. So if we want to establish a link between them, we have to resort to simulations where the most important physical effects are included. And this is why I call here the radiative gas dynamical simulations. What I mean by that is that So what I mean by that is that the simulation must include, of course, gravity by n-body, hydrodynamics of the gas, and also radiative physics, which includes all the phenomena acting on the due to the electromagnetic and atomic nature of the baryons. Now you know that there are plenty of you know that there are plenty of simulations now in the market with where they have extremely good accuracy in terms of reproducing the galaxy properties, different scales and redshifts, and include very sophisticated models to account for all these effects that I just mentioned. For example, the Illustris is very popular. But of course, if you include more and more physics and a higher and higher resolution, then you have to pay a price. The price is that you have to reduce your computational volume. So, for example, in the original Illustris simulation, you see that there are only of the order of 100 megaparsec box simulation, in which you can find hardly 5 clusters with masses bigger than 10 to the 14. Now you go to the TNG, to the next generation. The volume is bigger, 300 megaparsec, but still you have only like 20 clusters with masses above 4 times 10 to the 14. So not enough if you want to make a statistics of massive clusters, which are, by the way, the most interesting one, because these are the clusters that can better be observed at higher. Then, of course, the same thing happened in other projects. For example, the Eagle is again 100 megaparsec simulation, few clusters within the simulation box. The massive black is another kind of example. Horizon with Ramses AMR is again of the same order. All of them are of the same order, a few hundreds of megaparsec. Bahamas is computing a larger box, but with a much lower resolution, but a lot of different cosmologies. And of course, the Magneticum is one of the projects led by Klaus Dolack, in which a series of boxes with larger and larger computational volumes are produced. But still, as you see here, when the larger the box, the smaller the number, the smaller the mass resolution it is. And for the larger box, you hardly identify this internal structure of the galaxies within the cluster. Of course, if you're interested in producing light cones, there is no other way just to simulate the full box. Of course, the other alternative is just to go to dark matter only simulations, which are very cheap to produce in very large boxes, but then you have to add some additional ingredients, some additional recipes to go from dark matter to baryons. So either you use HUD for the galaxy, you use some semi-analytical modeling, or you use some kind of a scaling relation to relate the cluster, the halo mass, with the internal properties of the intercluster medium. There is an alternative, of course, when you are not interested in the full in the 3D distribution of baryons, and you are rather interested in having a catalog of simulated clusters in order to do statistics, to do calibration analysis of the different scaling relations and so on and so forth. We have heard many talks here during this week that large number of simulated clusters are needed. So one way to do that is just to simulate them individually, namely you just identify them in a very large volume simulation with dark matter only. Identify those halos with host clusters of the order of 10 to the 15 or above, and then identify from the particles, identify the regions in the initial conditions where these objects are formed, and then populate these areas in the initial conditions by baryons, and then degrade the rest of the particles of dark matter particles with higher and higher masses. So you reduce the effective number of particles, but still keep the gravitational evolution correct. So you just, by the end of the day, you will again reproduce the cluster in your simulated region. But this time in this zoom region, you can add more resolution if you want. You can just change the hydrodynamical code and just from the same initial conditions, you can just make different experiments about what is the effect of one or two or the other physics modules that you include in, or the effects of the parameters they representing the subgrid physics models, and so on and so forth. It's very flexible and also very parallelizable, because in that case, since each of these simulations is rather cheap to run, of course, much cheaper than the full box, then you can launch many different classes at the same time. You have sufficiently computer power. So by the end of the day, you will have a lot of different zoom regions where you have all the information, not only of the dark matter evolution, but also on the baryon properties and the stellar content and the black hole content and the chemical evolution and everything else. Of course, these zoom cluster simulations are very popular as well, and there are different groups that have been doing this kind of work. I will focus on these two last projects that this is where I was mostly involved. We started in the 2013 or so by creating this catalog of zoom simulation galaxy cluster we call MUSIC, multi-dark simulation of galaxy cluster. And so we have two sets of simulations. One was we used two different base simulations to select the objects. One was the Mare Nostrum universe, a 500 megaparsec gas dynamical simulation in which we selected the objects with, depending on the dynamical state, a bullet-like equivalent with and a relaxed one. And also we went to the first multi-dark simulation previous to the Planck cosmology. And then we selected 283 Lagrangian regions with a region around them of 6 megaparsecs. So the 283 most massive clusters were identified in the redshift 0 of this simulation, of the multi-dark WMAP7 simulation, were then rerun with baryons within a 6 megaparsec. So we found a lot of clusters in this way. And from this database, we did a lot of studies that I don't have time to to go into that detail, but you can see that in the Sembolini papers, which was the PhD student at that time that was in charge of analyzing all these kind of simulations. So, given the success of this kind of massive galaxy cluster or synthetic galaxy clusters, we also later on, after the famous NIFTY cluster comparison project, that you use one of the MUSIC clusters to do the comparison between many different hydrocodes. So we decided, a bunch of people that we gathered in these meetings, a bunch of people decided just to move forward and try to do like a second generation of the MUSIC with a much better simulations, right? So in this case, this is where we came up with the 300, because we simulated, instead of 283 like in MUSIC, we simulated 324 massive clusters, again centered on the most massive clusters at redshift 0 within this range of mass, with enough resolution of the order of 1.2 10 to the 9 solar masses per dark matter particle, and a force resolution of 6 kiloparsecs, plus some additional void regions, which are very extended regions, basically devoid of clusters or group of galaxies, but basically field galaxies. And now recently we have simulated these same regions, at least 1/3 of them, with higher resolution, namely 8 times more resolution than the original ones, but only in dark matter for the time being. But these initial conditions will be used then for simulating again with full hydro. Then from this data set of initial conditions, we run different hydrocodes, the gadget MUSIC, what was the original version of the gadget used for the MUSIC project, with no AGM feedback. Also the gadget X, which uses a modern SPH version, plus the feedback model developed by the Trieste people. And also very recently the Gizmo Simba, which is a completely different SPH code, and also a different AGM feedback model developed or based on Romil's Dabe. So from each of these simulations, we store 128 snapshots, and then we run AHF, the Amiga Allo Finder, to identify all the objects within each of these regions and all the properties within them, and also computed the merger trees, so we can study the mass accretion history of all these objects. Plus the mock observations. So we also simulated observations of all these clusters in different X-ray and different wavelengths, and lately, thanks to Max Meneghetti, the lensing properties.
You're in your last minute.
Sorry. Okay, so plus the addition that we have also using the multi-dark Planck simulation as the base simulation, we also have the sum results. The sum results for 3 different sum models. And in this paper, you can see that the comparison, for example, of the stellar mass, halo mass content predicted by the sum models compared with the hydrodynamical simulations. Now, very briefly, I just mentioned that we have a complete sample at redshift 0, so it means that at higher redshift we are losing massive objects, and here is just the mass limit, the completeness of the catalog that we have at different redshift. These are a typical example of the kind of mock simulation or mock observation that we have of all these objects. And from this database, there are plenty of different studies that has been made. 22 papers so far has been published, and you can link it. You can click in this link, and then you will see them. There are different analyses that has been presented in this conference as well. And if any one of you want to use this kind of this database or propose a project for that, I encourage you to go to the wiki project to request access to the wiki of the project, and then we will find the steering committee will evaluate your project, and then we'll decide whether you don't collide with other projects, and then you will have access to the data. I don't have time to go into the gizmo, but this, as I said, is completely different AGN feedback modeling, calibrated through a different set of to comply or just to fulfill the different set of observations. And these are the new data set that will eventually be incorporated into our existing data set that so far is based on the GadgetX results from the Trieste AGN feedback model. And well, I conclude just by saying that if everyone is interested, again, I want to stress that if everyone this collaboration is open to everybody, everyone interested in using it for a particular project, just contact us, please. Thank you. Sorry. Thank you very much.
Thank you so much, Gustavo.
Take your questions.
Wonderful. Are there any questions from the audience? It was a wonderful overview of a great data set. Glad to have access to that. I see Lindsay has the hand up.
I was just giving applause. Sorry.
Oh, sorry. I think I mistook the. Yes.
Thank you, Lindsay.
See, Johan has a hand up.
Hi, Gustavo.
Hi, Johan. How are you?
Good. How are you? So, will the data be public at some point?
Well, we're working on that. I mean, it's a problem just to make all this amount of data publicly available. I mean, in a kind of a database way. So far, the way we proceed is just again, you agree with the terms of the conditions of the collaboration, then you have access to the wiki, then you can see what kind of projects are going on, and you can propose a new project and ask for the kind of data product that you need for your particular project. And if it is accepted by the steering committee, then I will give you access. I guess you have access, or you had access before, to the computers here in Madrid, and then here we have basically all the data sets.
The particles.
We access to that, including the particles. Yes.
And okay, a secondary question: did you run different allo finders, so Rockstar, Subfind?
So far, well, yes, we have. Well, so far AHF is running all the simulations. Velociraptor is also being used now for analyzing some of the dynamical properties of the galaxies. and not Rockstar, because I mean Rockstar is, as you know, is mostly for box simulation and dark matter only.
Yeah.
And there is also a Galaxy version with where you can include different kinds of particles, but so far we haven't used it. No.
Okay. Thanks.
Great, thank you all. I think with the time we do have to move on to the next talk. Thank you so much, Gustavo, for that wonderful presentation. Next we have Elena Rasia. If you'd like to share slides.
Yeah.
Great. Elena will give us share some lessons on the hydrostatic mass bias.
Yeah, thank you. When Lindsay asked me the talk, the title about the talk, I say, okay, let's be ambitious and talk about lessons that we have learned. Then she told me that I have only 12 minutes and say, okay, from ambitious, I became ridiculous. It's impossible to talk about everything we have learned only in 12 minutes. So unfortunately, I have to focus only on 2 projects, one led by Saida Sarifard, published last year, and one from Julia Gianfagna, published at the beginning of this year, and then I will show some new work that are in preparation. So both projects are based on the 300 clusters that Gustavo just presented, and I've using only the code that has been developed by Trieste Munich, so is the Gadget X code. So the hydrostatic mass bias, just very basic idea. So we know that is there because we do observe the ICM through the X-ray. So the gravity is not dominating over the pressure, is not shrinking the cluster, and also the pressure of the gas is not expanding and pulling out all the gas. So you know that there is a certain equilibrium between gravity and pressure, and this is because we see clusters in the X-ray. And if we develop the hydrostatic equilibrium equation, what we have is the relation between the total mass of the system. So for total mass, I mean including all components, that is simply related to thermodynamical quantities like the temperature, the derivative of the gas density and the derivative of the temperature, or if you want, the gas density and the derivative of the thermal pressure. So this equation has been used a lot in the literature from many years, even a few decades, and we know very well that is a pressing problem to understand how well it goes. Indeed, a ban dedicated to the hydrostatic mass bias problem only a specific question in the poll, and the majority of us said that the bias is between 10%. The second choice was 20-30. I would say all of us, apart of a few people, said it's between 0 and 30%. This is actually also what the simulation are telling us. So this is a collection published, presented in the paper by Julia, where the last decade, I would say, works that are based on the hydrostatic mass bias are put all together, and we see that the bias is indeed between 10% and 30%, with the majority of the simulation being present between 10 and 20%. So I found this result and this comparison very astonishing. What these figures means is that different groups in the work using samples that are based in different hydrosolvers, because we have both SPH particle-based or mesh-based or even the moving mesh there repo. So independently of the hydrosolver, the answer is always very consistent. We also have that the mass range probing the different sample is very different. We go from very massive clusters in the BFI catalog to 10 to the 13 solar masses object studied by LeBron. The mass resolution is also quite different. We have a 2 order of magnitude variation from the illustris to the box 0 of the magneticum, and also the sample, the sample, the statistics, the number of clusters study is spanning from a few objects. We had just 3 objects in Meneghetti, and there are an order of thousands of objects in the box 0 and the Bahamas simulation. And independently of the hydrosolver, of the resolution of the simulation, of the groups that are doing the analysis, we always have that the bias is pretty much consistent between 10-30% with the majority simulation between 10 and 20. If you want to know, the average is 15%. This is also independent on the physics of the intercluster medium. So you see here that there are different colors. So those refer to simulation that have only non-radiative physics. They do have radiative physics, but not AGN feedback, or the dark blue are those with the AGN feedback. So for the rest of the talk, I will focus on the 300 simulation. So that is this box down here. And the first thing I want to check is if the 300 simulation are good to be used for this kind of work. So we saw that the total mass is related to the temperature, the slope of the gas density, slope of temperature, and this equation is valid at a particular radius. So if I'm interested to R500, I need to check if my simulation are while reproducing or not the observation at this radius. And we see that the slope of the gas density, slope of temperature, and the normalization of the temperature are while reproducing the observed data. So we can we can be safe to use this simulation for this investigation. So the first work we did was only using Redshift 0 clusters, and the goal of the work was to relate the mass bias to parameters that we can evaluate from the X-ray images of this object. So for this scope, we divided the clusters in 5 different classes, and they are all determined from the appearance, X-ray appearance. So there are very regular, which are centric, and very spherical, the regular, where also the center is very well defined, but we admit elliptical isoflux contour, and the irregular, where we might have some wobbling or small substructure. The other 2 classes that we do not consider in the paper are the very regular and the extremely irregular. System like the Bulle will be the extremely irregular, so very large substructure that are modifying the intercluster medium appearance. So if we separate then the cluster between these regular and irregular that are the color coded here, what we see is that the real difference between these 2 classes is not much the average value of the bias, but it's mostly the scatter of the distribution. So in the work, we wanted to see how we can reduce the scatter, but also, and most importantly, regularize the distribution of the bias. So what it's plotted here is the histogram, all the values of the bias that we have in these 3 classes, very regular, regular, and irregular. And as you can see, the peak is around 10% or 12% of bias, and there is quite a large scatter. We look at ways using parameters from the X-ray images, how we can regularize the distribution. And for that, what I mean is not only to move the mean to the 0 bias, because that would be trivial, you just add a constant. And for that, I mean not only to reduce the scatter, but most importantly, to make the distribution symmetric, so that you can to apply an easy model to the distribution of the bias. So the recipes that we studied and looking at only these 3 classes are actually working also for the very irregular clusters. So 2 examples are up here on the right. So starting from the bias distribution of the very irregular, if we correct them for the ellipticity of the image, we find out the distribution of the bias with as basically 0 skewness. Okay, so this was the first work, mostly focused on the X-ray appearance and what can we do from the observational point of view to understand a little bit better the bias. Instead of this work in preparation, we are looking more at the 3D quantities. So the analysis is extended to the entire sample, and at this point we don't separate the cluster between regular or irregular in the X-ray, but we look at the dynamical state parameters that are computed in 3D and using the whole volume of the simulation. So at this point the clusters are divided between relaxed and disturbed, and the object that before would have been in the very regular and the extremely irregular class and they were excluded in the paper before, here they are present present, and they are down here in the disturbed sector. So what we saw in this work, we extended to all the redshift. So as Gustavo said, the simulation is a resimulation of 300 region. We save several snapshots. They are 300 mega year apart. Here we look at all the snapshots that are 1 giga year apart, one of the other. And what we see is that more or less the bias is not dependent on the redshift. This is confirming a result that have already been published, again, using different codes and different hydro solvers. Within the mass range that we analyze, so we don't see a huge variation in mass. However, in this plot, pay attention that I'm putting together different redshifts. And so the red points that refer to redshift 1.3 are actually the progenitor of the green points of redshift 0. But even if you restrict yourself to the only one snapshot, you see that there is not a large variation in mass, even though the discussion, it's really when we go down in mass towards group scale to 10 to the 13 or even below. So this is something that we could check by extending the analysis to the secondary or tertiary objects in our Lagrangian region. So again, in this work, we are looking more at the 3D analysis. So we're looking at all the cluster. Here I'm plotting the bias versus these parameters, so the dynamical state parameters that tell us how much the cluster is relaxed or disturbed. And what you see by high is that even the by high, I mean that the mean value of the two samples is pretty similar, it's consistent, but what is really changing is the scatter around the bias that we have. And clearly, if we look at the same relation by using now, thank you, the mass growth, it's funny that the two plots seem like symmetric one to the other. So if you accrete a lot of mass, you're in the case of disturbed system, and you see that there is a huge variety, a huge scatter in the bias. So what in the second part of this work, what we focus on is really to understand why we have this negative bias that will be an overestimated bias. So if you apply the hydrostatic equilibrium equation, your mass will be greater than the true mass of the system. So to understand better this, we select 12 merging systems, and they are strongly merged, so it's one-to-one merger, and we stack them together accordingly at the time where the merger begins. So what we see is that during the merging phase, that is between this time called before and during the merger phase, the bias is always high, 25% or 30% or even more. So this is an average over the 12 system. But what we also detect is that after what we call here end, that is basically the end of the fast accretion phase. So it's when the secondary object is completely within the radius of the first object. So between this phase to the moment when the cluster is relaxed again, the bias has a huge bump, experiences a huge bump, it goes up and down. Also, it is in this phase that we have a negative bias. So what is actually going on here is that this work, as I told you before, is including all the clusters, so all the situation, also stream clusters, specifically these 12 objects are merging system, one-to-one merging system. And what we have is that when the substructure here is completely inside the radius, it's not that it immediately thermalizes and everything goes back to normal, but the structure has to move around the main halos before relaxing again. So there are situations like the one showing here on the bottom left, where the movement of the substructure creates a strong gas density gradient. And you see that all the objects have a positive bias. They also have a very strong gradient in the gas density. So to summarize this talk, So all the simulation are suggesting that more or less the bias is between 10-30%, especially 10-20%, I would say. So this is a strong signal because it's derived by different group, different hydrosolvers, different mass resolution, different sample, and different gas physics. Then you always need to a grain of salt to understand the result and what is given. So if you have a simulation that provides you a bias that is negative, so an overestimate, you have to consider the sample and how the cluster were selected in their sample, and also what is the physics in the simulation. So the large spread of bias is basically found in disturbed system, and this is mostly generated in the phase between the end of the fast accretion and the establishment of the relaxation phase again. Positive bias is present in disturbed system and mostly is linked to a steep gas density profile. Also pay attention that most of these objects might not be included in the observational sample. And so again, when you compare observation and simulation, you need not only to look at the techniques, the procedure that is applied in the simulation, but also how the sample is selected within the simulated sample. Thank you.
Wonderful. Thank you so much, Elena. Incredibly thorough studies in understanding the hydrostatic mass bias. I see we really only have time for one or two quick questions. So first I see Shantanu.
So this is just a very naive question. I guess the bias is defined by the total mass. Do we have separate handles for the bias of the dark matter as well as the bias of the gas mass? Or is it 0 for one of them?
No, so the idea behind the hydrostatic equilibrium is that the total gravitational potential is related to the gradient of the thermal pressure. So what the hydrostatic equilibrium tells you from at the beginning is that what you have from the thermal components is really the total mass. So you can now really distinguish between the two components.
Okay, thank you.
Great. Just due to time, if both Wonky and Gary, if you can put your questions in the chat, perhaps then Elena can see those just so we can stay on time with the next speaker. Thank you. Sorry, we just ran a little short in time, but thank you so much, Elena, for that wonderful talk. Our third speaker is Qingyang Li. If you could, oh, wonderful. Great. Thanks. Who will tell us about what we will expect from dynamical modeling of cluster halos. Take it away.
Yeah, okay. Hello, everyone. I'm Qingyang Li, a PhD student from Shanghai Jianheng University. I'm glad to give us a talk on our recent work. So we try to understand what can we learn from the dynamical models. So besides weak lensing, perhaps the dynamical models is the most popular class mass estimators. So the traditional dynamical methods include such as Jeans equation, various theorem, caustic method, and hydrostatic equilibrium. So those methods have been widely applied in simulations and observations. So while those applications give us valuable results, it's not easy to get a conscious and consistent understanding of the systematics which caused by the various particular assumptions, especially for the steady state and the spherical symmetry. So here we apply a generic minimal assumption method, OPDF, the orbital probability density function, to study this question. So the OPDF is a steady state solution to collisionless Boltzmann equation. So the idea behind this method is that if a system is in a steady state, so along a given orbit, the probability of observing a particle near its position is proportional to the time it spends at this position. So if we take a particle as a car, so and the crowded road, we would expect to see more cars, which corresponds to the high density. So in practice, we input the velocity and the coordinates of particles to the OPDF, then we can get a parameterized potential profiles. We compare this modeled profiles to a true profile. We can infer the mass and concentration of the cluster halos. So in this work, we consider three different tracers: the dark matters, halo stars, and the satellite galaxies, with the data from the hydrodynamical simulation in the 300 project. So first, we apply the OPDF to the dark matters. So for each cluster, we randomly selected 10 to 5 dark matter particles from the which not bound to any subhalos to avoid the contamination of substructures. So those tracers are distributed from the 200 kilopascal to the Weyl theorem. So as you see in this figure, the best fittings for the clusters shown with those green poles are stochastic and largely ensemble unbiased. The dispersion of these mass estimates is about 0.17 dex. We also compare with the galactic halos. So you can see the galactic halos shown with those black triangles give us small deviations, which can be explained that the galactic halos are formed earlier and they can reach the steady state earlier. So on the right top panel, we show this steady state error, which is rather small than the total scatter, and both of them have the same direction. So how to understand the relation between the statistical error and the total scatter? Here we bring in the idea that the number of phase-independent particles. The tracers used in this model are correlated in the phase space. So for example, the particles stripped from the same progenitor share the similar orbits and similar coordinates in the phase space. So those the strong phase correlations are from the stripped particles, which result in a small number, effective number of phase-independent particles. That means those strong phase correlations will reduce the effective dynamical informations. But remember that the strong correlations is also deviate from the steady state, causing the systematics. So you can see as this animated figures, the particles in a steady state are distributed evenly. Then we also apply the OPDF to the intracluster stars and satellites. So those results can also explained by the idea that the effective of number of independent particles. So in the right panel, we compare the those three different tracers. So we can see the dark matter and satellite galaxy share the closed dispersion, while the halo stars give a larger scatter. So the fitting results reflect deviation from the steady state in the tracers. So from this dispersion, we can see that the dynamic state of the satellite galaxy is close to the dark matters, while the halo stars is less relaxed. So we also calculate the cluster mass with gas particles. So the results shows that the gas is also a good tracer. So our main result is from the OPDF. We also try other dynamic models, such as the general hydrostatic equilibrium and the spherical Ginzzi equation. So those estimations give the similar results with the OPDF. The deviation of the best fitting halo stars and the concentration parameters are all anti-correlated and vary stochastically from halo to halo. and the estimation on the mass is comparable. So we have different results from the different dynamic models. So how to understand those results? We also provide the idea, the efficiency, and the robustness. That the phase-independent particles provide effective dynamical information, as I explained for the dark matter particles. So the different models have the different efficiency and robustness in use this dynamical information. So the efficiency means the statistical error. So you can see the left panel, high efficiency dynamic models will give a smaller statistical error. The robustness means the ability of the dynamic models to recover the number of the phase-independent particles. So with those two definitions, we can quantify the total scatter as this equation shows. So despite those differences, our conclusions from the OPDF are largely applicable to the other steady state dynamic models. So this is a serious work. So in this work, we compare the different dynamical state in the different dynamic tracers. So what else can we expect from the dynamic models? So in this figure, the relaxed clusters give a rather smaller scatter than the unrelaxed cluster in both the OPDF and the spherical Gaussian equation estimators. So this tells us first, our results, OPDF results can also apply in other models like the spherical Gaussian equation. And second, we can use some quantities to link the best fittings from the dynamic models to the dynamic state of the clusters. So a follow-up study will focus on this project. We try to investigate the different properties of the dynamical state. So here's the summary. So in this work, we study how well the underlying gravitational potential of the galaxy clusters can be modeled with different tracers. So we can see that the halo mass and concentrations can be recovered in an ensemble unbiased way. And we use the dark matter satellites and intra-cluster stars and tracers. The dynamic state of the satellite galaxies are close to that of dark matters, while the intra-cluster stars are less in a steady state. So finally, our results are also can be applicable to other steady state dynamic models by quantitatively segregating the static efficiency and the robustness to the systematics. So thanks.
Great, wonderful. Thank you also for those wonderfully on time. Thank you, Qingyang. So do we have questions from the audience? I see a hand up from Gary. Go ahead.
Okay, that was very interesting, Qingyang. I just want to make a couple of comments. So one, your method of using some idea on the orbits is very interesting. And I wanted to highlight a work that was done many years ago by a Russian person working on gamma rays, I forgot his name, who had a paper called the roulette. And in the roulette, he assumed that the phase on the orbit was random. And he argued that you could learn a lot by doing this. But he only considered the case of a point mass potential to try to weigh a black hole, if you want. So that's a dynamical roulette. And then one thing you can add is in the genes modeling is you can add velocity anisotropy. And so when we did this with Andrea Biviano, with Mampost in 2013, we found that with much fewer particles, 500 instead of 10 to the 5, we were getting a better accuracy on the mass. Not fantastic, 0.12 dex instead of 0.17. But as you highlighted, we have systematic errors. And so This is what we showed in the discussion on the first session, is that you can plot, and as Radek mentioned, and Dugesh, is that you have a systematic error and a statistical error. And some methods just can beat the systematics, in particular some neural network methods. All right. It seems to me that that's the way to go for dynamical modeling, because they will account for more information than we thought about.
Yeah. Okay. Thanks a lot.
What do you think about that, about the machine learning methods?
You mean use machine learning to extract the dynamical information?
Yes, yes.
Actually, so I recently I use the machine learning to study the follow-up study, but I haven't thought about this idea. So
yeah, look at Dugesh's talk on if you can get the recording of it.
Okay, we can talk. Yeah, we can talk it later. Yeah.
Yes. Thank you.
Thanks.
We have time for any other super quick question at the tail end. Okay, it's great. It sounds like there's like new project ideas coming out of these discussions. So thank you so much, Qingyang. And next, our fourth speaker is Dhayaa Anbajagane. So if you can please share your slides, and Dhayaa will be presenting on the galaxy velocity bias. So take it away. It's great to hear this.
All right. So I'm assuming you can see this. You can hear me. You can see the slides move. Okay. Yeah. Okay. Thank you. So hi, everybody. I am Dhayaa. I am a second-year PhD student at UChicago, and today I'm presenting work on velocity bias in HydroSims, as the title slide says. And this is in collaboration with a number of people who are on this call who I've listed below. So what are the goals of this work? Over the 4 days of this conference, we've spoken a number of times about this M-sigma relation, where sigma is this dispersion. So it's a second moment or a standard deviation of a velocity distribution. Could be either of the galaxies, could be of the dark matter. And so the galaxy dispersion is what you actually observe. The galaxies are what you need to use to infer what the dark matter is doing. And very analogous to how there's a clustering bias between galaxies and dark matter, there's a velocity bias between the galaxies and dark matter. And so in this work, we're trying to calibrate what this bias is as a function of different things. But the novel thing that we're doing, or the interesting thing that we're doing, is also quoting what the astrophysical uncertainty or the model uncertainty on this is. So the way we're doing this is by taking an ensemble of simulations, seeing what the predictions of those simulations are, and then using that to set a prior on what the mean bias and the uncertainty on that bias actually is. And so this bias is defined as just the ratio of the different dispersions, the galaxy dispersion, the dark matter dispersion. So in the pursuit of doing this, we'll also do comparisons between those dispersions in the different sims. And finally, at the end, I'll give you an example as a way of illustrating how much better we can do with mass calibration, given some information that we're getting from the sims, specifically this prior. And I don't think I have to explain this too much. Gustavo helped me out a lot by listing out all of these simulations and the pretty pictures from them. So I'm using 4 different hydro sims. I have a 1 n-body sim with the semi-analytic model, which I'm only using for a small part of the analysis. All the bias stuff is just going to come from the simulations that Gustavo listed before. And the 300 project, since Gustavo mentioned this, I'm using the Gadget X run, not the Gadget Simba run or the Gadget Music run. All right. And for those of you who are familiar with computing sigma gal, you know that since I mentioned it, I also have to mention how I'm actually computing it, since there are many different techniques, all with different pros and cons. The fundamental issue is that the simplest way you can think about doing this is taking the galaxies you have in a cluster, just taking the standard deviation of them to estimate a dispersion and then running a linear fit on that. There are a number of issues associated with that. One of the issues is how do you quantify what the uncertainty on your estimate is? If I have only 3 galaxies, how am I going to quantify what the uncertainty on my sigma is? And so the way we're getting around all of that is by doing this from a likelihood perspective. And so this likelihood is written to what is the likelihood of a galaxy velocity given a host halo mass. And there are 2 components to this likelihood, host halo mass and the number of scaling radiation parameters. And there are 2 components to this. One is just the regular Gaussian. So galaxy velocities in a halo follow a Gaussian form. And there's also a log normal component that tells you what is the distribution of dispersions that you can have given a halo mass and a particular scaling relation. And the scaling relation parameters are really what we want. So this is just a standard normalization and then a slope factor. And so this went by too fast. You're not too familiar with this. All you need to know is we're using a likelihood, we're getting a scaling relation, and the parameters of that scaling relation are what we're interested in. So this is the figure, one of the key plots from that analysis. There's a lot going on here, a lot of different points. The top panel is what I would start focusing on. So these are the normalizations we talked about in DEC. And as you move from left to right, the results come from galaxy samples that had a higher and higher stellar mass threshold. So those are the labels given on the bottom. And the different colors of the different sims, different color tones are different redshifts. So what you see is as you move to the right, the normalization of this relation is decreasing as you select more and more massive galaxies. And this is nothing new. This effect has been known for a while. It's called brighter to cooler. More massive galaxies are kinematically cooler. In fact, the first paper I can find on this goes back 30 years almost to Andrea's paper in 1992. So we've known about this for quite a while. The other thing I'll point out is that for the slopes, all of the slopes, there's a stellar mass dependence, but more importantly, they're all above 1/3. So 1/3 is the number that we see quite often when we talk about the M sigma relation with dark matter. And with galaxies, we find that they're consistently about 1/3. And this will be important when we talk about the bias. All right, so there's a number of other things we could talk about here, but I'll skip this in the interest of time. And now moving to the sigma DM, which is the other component for the bias, we don't have the uncertainty problem anymore. And so we can just do a regression. I'm doing a local linear regression so that I can capture any nonlinear features in the scaling relation. The way this works is you weight all halos by a Gaussian kernel and you do the regular linear fitting. And as you move this kernel over mass, you get mass localized estimates for the slope and the normalized or the means. So here's the result from that. So once again, there are a number of panels here. I'll focus on the second and the third one. The second one is showing you what is the fractional difference between the simulation's results and the Everard-08 prediction. So that was a scaling relation that came from a number of dark matter simulations, very precise relation. And so the gray bands here are the uncertainties from the Everard-08 relation. And in general, the simulations agree pretty well. There tends to be more discrepancy as you move to the lower masses. Bahamas goes up a little bit, the 300 goes up a lot more. And in the slopes, this has an associated decrease where as you move to lower masses, the slopes decrease below 1/3. And this is seen systematically in all the different simulations. And in fact, we recently put out a paper yesterday morning where we studied this effect in TNG 300, not 300. And we found that it comes about because of different galaxy formation processes. So different cooling and feedback mechanisms induce this sort of feature. And this shows up in many different dark matter properties, but in terms of sigma DM, this is how it manifests. All right. So finally, I get to the bias, what I started out with, the main goal for this project. So the bias is now just being defined as taking the mean scaling relations for the galaxy and the dark matter, and then just taking the ratio of them. How different are these two mean relations? And the different panels are just showing the bias as a function of mass, but different stellar mass threshold. So the stellar mass dependence comes purely from sigma gal, and these are both at redshift 0. So the first thing that's very obvious, hopefully, is that there's a very clear mass dependence, and this comes about because there's that slope mismatch. So the galaxies have a steeper slope, and then the dark matter has a slope of just 1/3 or even lower. And so if you worry about calibrating the bias at 1%, then you need to think about the mass dependence. You can't run away from that. And the other thing that might be obvious is that the simulations are generally in pretty good agreement. So there's no 30, 40% difference. It's much less than that. The one thing that might catch your eye is that this blue curve is a little higher on this plot than these others. That's just an unfortunate choice of plotting because at this particular redshift, this particular stellar mass is a lot more pronounced of an effect. In general, the agreement between the sims is about 2 to 3% precision over at specific halo masses, stellar masses, etc. And of course, the uncertainty goes up by a lot when you go to high redshift or high mass or high stellar mass because your sample statistics or your sample size is low, so your statistics are poor. And if you remove the Bahamas and Maxis line, so if you remove the blue line, then generally all the uncertainties are the uncertainty in your astrophysical uncertainty is going down to 1%, a little lower than 1%. And so at first, this might seem not poorly motivated in that, oh, you saw a blue line that was discrepant, so you just removed it. One of the motivations we have for doing this is that we study the impact of resolution on this using the TNG suite. And thankfully for us, one of the TNG resolutions is pretty similar to Bahamas and Naxos. And we found that most of the resolutions agreed very well, except the poorest TNG resolution, where the dispersion was actually amplified. So that might have something to do with how dynamical friction is really affecting these if you have fewer particles. But in general, there's some indication that Bahamas and Naxos might have some resolution-dependent amplification, but we're not completely clear on this, which is also why my talk is titled Towards 1% rather than just 1% itself. And so that's one point there. Now, the last thing that I said I would do is tell you how improvements in this bias can improve our mass calibration. So for this, I'm just going to run through an example. We're redoing an exercise from a previous work, Farahi 2016, where they took an SDSS sample, red mapper sample with spectroscopy, and they constrained a dispersion richness relation first. So that's this equation here. Once you get the pivot dispersion, you can use a bias to convert that to a dark matter dispersion. And then once you have the dark matter dispersion, you assume a scaling relation, the FR to weight relation, and then you get a mass out. So those are the 3 steps. So we're keeping all of this the same measurement, same process. The only part we're going to be changing is this bias term. So I haven't mentioned the GUO work before. So this work used a halo model approach, fit small scale RSDs and infer the bias from that. There are a couple of issues with this, one just being much larger uncertainties, normally 6 to 8%. But more importantly, they found that more massive galaxies actually have—
3 minutes.
Thank you.
Yeah, just 3 minutes.
Yeah, they found that more massive galaxies actually have a higher velocity dispersion or a higher velocity bias, which is really weird because it goes against 30 years of work that have been done on clusters. So there's either some systematic in the RSDs that's causing an issue, or the sample that they're studying might not pertain to cluster science, one of the two. But regardless, there's a need to replace that, which is where this work is coming in. So that's the only number that we're going to be replacing. Everything else stays the same. We're just replacing the GUO result with our theory prior. So when we do that, this is our money plot on that front. So the left panel is showing you the normalization of the mass richness relation. The right panel is showing you the uncertainties. So the uncertainties are the same as the bars. The right panel is just a nicer way of looking at it. The first 2 points are our results from this work, updating the Farahi 2016 paper, which is shown in green. The next 3 are just a sampling of other results from literature on constraining this relation using different samples and different techniques. So the 2 things I'll point out is that the Farahi 2016 result had a 22% uncertainty, and 21% of that came from just the bias. And now with the updated theory prior from our work, we're able to bring that normalization uncertainty down to about 7 to 8%. So about a factor of 3 increase. This doesn't put us, the plot makes it seem like we're doing better than weak lensing. This is sort of a trick in that for the McClintock work, for Chen Hao's work he presented on Monday, we're actually quoting those normalizations away from their pivot mass. So the uncertainties that are quoted here also have the uncertainties in the slopes folded in. In general, at the pivot mass, McClintock and Toe 2020 have about 5% uncertainty, a little bit lower. So we're not better than lensing, that would be impressive, but we've gone from being 4 times worse to being about order factor of 1 close to their uncertainties. And so the uncertainty in these estimates for this particular analysis now is dominated by the statistical error, which will go down as you get more data, and a systematic error in the central galaxy velocity bias. And that comes about because you can't get satellite halo velocity pairs. You need to use the central galaxy. And so the central galaxy's bias also folds into the analysis. All right. And yeah, that's everything that I have for you. I'll leave you on my summary slide, and thank you for listening. And if there are any questions, I can take them.
Wonderful. Thank you so much, Dhayaa. So I see 2 questions, one from Gary and another from, oh wait, I think that Lindsay's is the applause. So yes, applause. Gary, go ahead.
Thank you, Lindsay.
Okay, I just wanted to go, this is very nice, first of all, it's very impressive. And I just wanted to go back to your very first plot where you were doing the galaxies and you showed the likelihood formula.
Right.
This one. So I'd like to make 2 comments here. One is on the fact that if you had no prior and you just did maximum likelihood and you had 3 or 4 galaxies only, then maximum likelihood is biased. Okay, and this has been shown by several people. Laporte et al. By 2019 maybe showed this with Monte Carlos after that. And then the left part, the Gaussian assumption for, if I understood correctly, the Vij are the line of sight velocities, right?
Yes, they're the line of sight velocities.
So the line of sight velocities are not necessarily Gaussian, right? They're more Gaussian if you're isotropic. But if you're anisotropic, if you have radial orbits like we do have outside, somewhat radial, then they're more cuspy distributions. So in the end, you have very nice results. So so it might cancel out because of the second term. But so one can find ways of doing better. One way is the Mampost method that we do with Andrea, and there are other methods to calculate what it. And so what Mampost assumes is that the three-dimensional velocity distribution is Gaussian, which is already much better. Okay.
Okay, I understand. So you're just talking about, this is not considering interlopers or anything, just the pure
exactly.
true population, right?
Yes,
Okay, got it.
But
Thank you,
otherwise,
that's
it's very nice work.
Thank you.
Great. Any other questions from folks? Okay, I don't see any. Thank you so much, Dhayaa, for that wonderful talk and presentation. All right, so next up, we have our final speaker, who is Riccardo Seppi. You can start your screen share.
Yes.
Is great, thank you. So Riccardo will tell us about the mass function dependence on halodynamical state. Take it away, thank you.
Yes. Hi everyone. I assume you are all seeing the slides and hearing me. Otherwise, let me know. I want to thank the organizers first for giving me the opportunity to present this talk. I'm Riccardo, second-year PhD student at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany.
Riccardo, the sound is a bit weak. Is there a way you get closer to the microphone?
Is it any better?
Yes, no.
Let's see.
Yeah, it
gives me problem if.
But it's noisy, not too much.
Like this. I'll try to be as loud as I can.
That is good, I think, yeah.
Yes.
Yes. So yeah, so I work on and I am part of the Eurosita consortium. So I always like to show this beautiful figure of
sorry, I think it is weak again, unless other people can still hear.
No.
No. And if I turn my volume up.
Let's see. What about now?
Yes, that's better than the previous. Let's see, I think it just faded away after the first like 10 seconds of you speaking. But you can try this. I think now is perhaps better.
Okay. Yeah, I hope it's
not better.
Oh, it lost again, I think.
Yeah, it seems that Zoom resets the volume when you change it and put it back low at low value.
Is it any better?
Yes, that is better, but let's try this.
Let's see.
Much better.
That's good,
Okay.
yes.
Okay. Yeah. Okay, I'm sorry about this. Yes, so yeah, so today I will talk about this new model for the halo mass function that we developed. And the talk is based on a paper that has been published on ANA, so you can also find it online. So here is a brief outline of the presentation with a short introduction about clusters cosmology and the impact of selection effects on this topic. Then we will see some mean relations that we calibrated between halo properties and mass using n-body simulations. And I show one of the snapshots that we used here on the right, available at the CosmoSim database. And then the focal point of the whole work is this generalized halo mass function framework that allows to include parameters describing dynamical state of dark matter halos. And then finally, a possible link to observations for our theoretical n-body only model. So clusters cosmology, I'll be fast on this, I'm sure we are all familiar with it.
So we see in this figure from Borgani and Kravtsov two different types of universe, lambda CDM in the top panels and the Einstein in the sitter. They reproduce a similar large-scale structure at redshift 0, but the evolution to get there is quite different. So basically the evolution of halo abundance throughout the cosmic history of the universe is a great cosmological probe. And this is translated into this equation for the mass function that depends on cosmological parameters. And we can also see this in the plot on the right, where we have the mass function at two different redshifts, and the solid lines is the fiducial Planck cosmology. And then as soon as we change omega m and sigma 8, the mass function changes accordingly. But of course, to do all of this, to do cosmology with clusters of galaxies, we need a well-defined sample. So we need to know whether we are detecting all the clusters that are out there, or we are systematically missing some of them. And so for us, working with X-rays and Rosita, our observations suffer from the cool core bias. So what happens is that dynamically relaxed clusters developed an efficient cooling towards the central region, which translates in a peak of the surface brightness profile towards the center. And this biases the detection towards these objects compared to unrelaxed ones that did not develop an efficient cooling and are lacking this peak in the brightness profile. So this effect depends indeed on the dynamical state of the dark matter halo hosting such clusters. So the idea was to calibrate a new model for the mass function that includes parameters describing the dynamical state. And we use the multi-dark set of n-body simulations. And here on the left, I show the entire halo population in the spin offset parameter space. And this offset parameter, xof, is of particular interest. This is basically the offset between the center of mass of the dark matter halo and the peak of its density profile. So it's a measure of how disturbed the structure is. And we apply two cuts to separate a relaxed and unrelaxed sample. And then here on the right, you can see the different contributions that these two populations give to the total mass function. The low mass end is dominated by relaxed structures, and then at the high mass end, the unrelaxed ones take over. And if you have a different selection between these two populations, this will change the shape of your mass function and bias the cosmological results that you can get in a cluster count experiment. To deal with this, first of all, what we do is to assess mean relations and distributions between halo properties and mass. So here I show the spin to mass relation. We parameterize it considering sigma, the variance of the density field, instead of mass explicitly. It's a simple linear relation. And on top of this, we model the distribution of spin around its mean value with its PDF, its probability density function, with a modified Schechter equation at 4 different redshifts. Similarly, we have the offset mass relation. This time it's a bit more complicated than a linear relation. Here is the equation, but again, the PDF is a modified Schechter function. And I wanted to show these individual models because what we do is combining them into a generalized mass function framework, where now we are measuring the number density of dark matter halos, not only as a function of mass, but also as a function of these two additional parameters that I introduced, xof and spin, which results in this equation, very similar to the mass function, the classical mass function equation, with the addition of these two parameters, basically. And with this approach, what you can do is then integrate this H function once to get 2D distributions that we call G. And you can marginalize once again to obtain 1D distributions that we call F. And with this formalism, you see we are able to recover the F sigma, the multiplicity function, the one commonly used in mass function models, except that now it has been marginalized on dynamical state. So it allows to account for a selection based on dynamical parameters. So here you see the equation for this model. It's a combination of different power laws and exponential cutoffs, combining the individual modified Schechter functions with some cross-dependent terms. But the main point is that if we look at all these plots that are different combinations of the 2D distributions, we see how the model is able to recover all the features that we see in the simulations quite well. And in particular, we focus here in on this plot on the left. This is the multiplicity function marginalized on dynamical state. And we compare our result in blue to the black line, the Compara 2017, which is the fiducial mass function for this set of simulations. We see that they agree within 3%, also at very high mass. And this is great because it means that we have a model that is also accounting for dynamical state of dark matter halos that is able to recover the proper mass function. And on top of this, we also account for redshift evolution up to redshift 1.4, and we provide a parameterization of all the parameters describing this H function. Now the next step is how do we link our model to observations? And the idea is that if we are able to understand our selection in terms of XOF, then we can just marginalize our 2D model to recover an unbiased multiplicity function. And since XOF is basically a displacement, as I introduced before, the idea is to compare it to the distance between the X-ray center and the optical center in eROSITA clusters, using, for example, the position of the BCG or an average considering all the cluster members. And one first implementation is shown here on the left for IFEDS clusters. This is a mini survey that has been done to check the eROSITA performance, basically. And we show
3 minutes.
Thank you. And we show the cumulative distribution functions for our model and for these two distributions. This is still in development, and what we are also doing is using using hydro simulations like TNG or Magneticum to try and build this bridge between the n-body world and the theoretical models and what we can see and measure in data and observations. So here is a brief summary. I hope I was clear in showing that the dynamical state of dark matter halos has an important impact on the mass function and how the different individual models can be combined into a generalized framework to marginalize over dynamical state in cluster count experiments. Before closing, let me just say that this model, this mass function model, has been implemented in the Colossus package. If you don't know it, it's a Python package commonly used for cosmological calculations developed by Benedict Timmer. So if you're interested, you can just have a look and use this model. And yeah, so with this, I would like to thank you, and I'm happy to take questions if you have any.
Wonderful. Thank you, Riccardo. Right on time. See, do we have questions from the audience? Sorry, my internet's bad, so I have to sort of, I'm calling on my phone, so I have to switch off Windows slightly awkwardly. Do I see any hands? guess I have a question, Riccardo. You talked a little bit about connecting this to observations, and you're using XOF as a criterion. So would you, in terms of extending this analysis, then I think you might have touched on this, but in terms of extending this to observables like with full hydrosims, use I guess X-ray signatures of relaxation or otherwise, in terms of doing that kind of a link?
Yes.
Or yes.
Yeah, so what I'm doing now is using hydro simulations like Magneticum and TNG, and I'm looking for some observables that are correlating similarly, let's say, with XOF and to the optical and X-ray displacement. So for example, I'm seeing that the star formation rate of the BCG does correlate with XOF. So the next step is to check whether it has a similar correlation to the displacement between X-ray and optical centers. So that then we could basically correct for this shape of the mass function using, for example, in this case, the star formation rate of the BCG. But yeah, exactly. That's the goal, to try and use the hydro simulations to measure XOF on the n-body side, and then measure some observables the same way we do in data, to build this bridge between data and the n-body only model.
Okay, cool, great. That's a nice approach. Thank you. Just flip back. I see a question from Ben. Go ahead.
Hi, thanks. That was really interesting. I liked seeing how the different dynamical states contributed to the mass function. I haven't seen that before. And this is more of a comment, really. It highlights the issue, doesn't it? That at the high mass end, where some of the most leverage is, that's where we're getting dominated by the dynamically disturbed clusters, that we have the most difficulty, A, defining what we mean by their mass, and then B, actually measuring their masses. I wondered if you had any thoughts on that.
Yeah, absolutely. Well, I guess that's the whole point, because the most massive ones are the recently merged, so it's that's why they are unrelaxed in first place, right? So yeah, the main problem is the selection, as I was saying in the beginning, and try to figure out how we are exactly selecting all these unrelaxed clusters.
Yeah, I mean, you're quite right. You sort of highlight the importance of that. If we're not even selecting them in the first place, then we don't even have to worry about getting their masses wrong.
Yes, and I guess this goes back to all the talks that we had in the previous days about selection function, which is of course crucial, especially at this high mass end, because it's where the mass function is changing exponentially. So we have a lot of sensitivity on cosmology in this range.
Great, wonderful. Thank you so much for that wonderful talk, Riccardo. I think given time, it's probably the point where we should transition over to the discussion, with some of which has already started in the Q&A. So thank you everyone for that. And I think, so Gus, I think you are online and able to screen share. Apologies for having to switch to my phone, so I'm unable to do the screen sharing effectively.
Yeah, I try.
Oh, yeah. Oh, great. Yeah, if you can do that, that'd be awesome. Thank you.
Okay. So could you see my screen?
Yeah.
Yes.
Okay.
Gus is muted, just so you know.
So I don't know if Gus is online.
He is, but he is muted.
Now I'm unmuted.
Yeah.
Sorry.
So maybe you can go ahead and start, and then.
Sure. So this has been a really stimulating meeting. I wish that we could be together physically to be even more stimulated than we are by being together virtually. But let's try to, what we thought we would do, Camille and Barbara and I, is to sort of frame a few questions for participants who are still online to address. And if we could go to the next slide, yes. So, key element in terms of what we're trying to do in cluster cosmology and cluster astrophysics is to understand what the theoretical expectations are of the massive halo population in a lambda CDM or otherwise universe. And so trust is an inherent aspect of all of this that is really lying at the heart of our business, in the sense that galaxy clusters represent massive halos that are strongly nonlinear. And how do we generate accurate theoretical expectations for phenomenon in the strongly nonlinear regime of structure formation? And here I'm just going to steal Hank's lovely virtuous circle slide, but point out that I'm a little confused about, I love the 4 elements. I'm a little confused about the arrows because when you think about it, from observations, we get mass proxies, right? Not actual masses. And so there's a line that's kind of missing, which is a line that connects simulations to masses, because only in simulations can we actually get that 3D halo masses, the true spherical overdensity masses that the mass function, halo mass function, is tied to. So the first question that we'd like to pose to audience members now is, there's this fundamental disconnect. We can never go out and send a satellite out to Abell 2163 and encircle it with a big sphere and actually take an accelerometer or something and measure the mass. So we have all these mass proxies that we can get from photons. How do we convince our physicist colleagues or our astronomer colleagues that we can estimate true masses, the true things in the simulations, to X%, where, as we learned from Henk a few days ago, the data quality is going to get to the point where those X's will be very small, less than 1% potentially. So I'm going to throw that out, and maybe Barbara or Camila, you can kind of take a look and see who wants to.
Yeah, I mean,
feel free to unmute and join in, or you guys can feel free to comment and join in right now.
Yeah, I think the main point is to understand how really we are at the point that if we want cluster to be competitive with the other cosmological probes, we have really to use simulation to understand data. So, okay, you have the true mass from simulations, but then you have to go as nearer as possible to the real observable. So like, I don't know, you have like from weak lensing, you can derive like projected masses. So maybe from simulation, you also have to go to produce 3D masses, but also to produce something that it's nearer to real data.
This was Marguerite Pierre's comment.
Mm-mm.
We don't need masses, we just need proxies.
Mm-mm.
Good, Gary. I'm happy that at least someone.
No, we've been talking about this.
Point.
We've been talking at this at Euclid meetings years ago. Yes, it's. I think Hank brought it up. I forget who it was, and I thought it was a great idea.
So but then what I see as problematic are 2 things. First of all, there's been a lot of work on calibrating the mass function using dark matter only n-body simulations, emulation campaigns, etc. There's been no similar emulator campaigns focused on mass proxies.
Yeah, and we don't know whether we'll get the mass proxies to the same precision as we're getting the halo mass function today, even though it's not perfect and it depends on baryons. But maybe the proxies will come out to be worse. I don't know. Or maybe it'll be just the same, in which case we should go for the proxies.
I see Tim's hand up. Yeah, I mean, I think the link is really weak lensing, right? I mean, you need to use the same simulation which you use to generate the mass function to also emulate your lensing data. And that's basically what we do for the weak lensing mass modeling calibration. So as long as you can get the selection sufficiently well understood, I think that's really what is the solution. I mean, there's of course the tricky bit that the baryons change your density profiles for lensing, but the way to get around this is trying to calibrate this via the hydro, which basically should have the same condition otherwise as the dark matter only simulations. And then the only question is how good is the hydro to get your density profiles right? And that's where the idea is to use the range of hydro simulations which are there and see how big the impact is. And we see it's relatively small, right? It's at maybe the 2% systematic uncertainty, which is like, say, what's argued in the paper from Sebastian Grandes. And so that would be my suggestion.
That's a very good point.
Just to respond to that, that was two examples. Those were two simulations, right? So can we really say the spread is 2% when we've compared two simulations?
No, I mean, you would of course want to go through a wider range of simulations, but then the other thing you can also do is you can use the lensing data to check the actual density profiles, right? The concentration distribution, and see is what you basically measure on the real data, is that consistent with what you expect from the hydro simulations? So that's a cross check you can do. This is a bit degenerate with your uncertainty on the miscentering, because that also affects your lensing measurements at small scales. So you have to look at those things together. But I'm optimistic that we can get to the percent level accuracy there at least.
Johan?
Yes, I'd like to add to that dynamical information using large numbers of galaxy redshifts in clusters are also a key to infer dynamical masses and then masses. So I guess a combination of dynamical information on galaxies and weak lensing would even be stronger, because it's prone to different, let's say, problems or systematics.
Daisuke.
Yes. So I think maybe the first area that we really need to push on is a suite of cluster simulations with baryons for a wide range of astrophysical parameters and cosmological parameters. They don't exist. But I think that something like this starts to happen on smaller boxes. For example, the camel simulations is a project where the multiple code has been used in including subgrid physics, and start to do the simulation over the large range of astrophysical parameter space as well as cosmological parameter space. Right now, I think the box size is about 25 megaparsec-ish range. So it's a little small for cluster cosmology, but things like that, I think it starts to become feasible. So I think what we can hope to do is to kind of do more of this, but scale up the calculations. And I think to start to do that on group scale and eventually the cluster scale, maybe zooming simulation may be the way to go for a starter. So I think that's one program I think that we really need to push on, is to maybe think about doing zoom-in simulation for a wide range of astrophysical parameter and cosmological parameter space. So I think that's sort of a new frontier in computational cluster cosmology. Maybe the second aspect is, I think some of the audience have actually said that we can't probably really rely literally on any realizations of the simulation, but maybe what we need to understand is the ingredient that actually affects them. For example, things like mass estimation or selection functions, but not like this specific realization of particular features in clusters. So maybe one way to think about this is to actually do forward modeling, where some of the key ingredients like shape of the halo, velocity anisotropies, X-ray properties, profiles, these are parameterized, and you really just need to focus on how to model those, forward model everything. I think that includes understanding the distribution within the halo properties, and then also observational scatter, which could be modeled by actually, for example, painting some of those halo model type approach that includes sufficient complexities and realistic sort of features like shapes and profiles. And then, dependence on mass accretion rate got talked about a lot. And all of that is, in principle, we are getting an understanding of it, so we can incorporate those into the halo type model type approach, and then but put that into light cone simulations so that we can model things like two halo term, projection effect, miscentering. I think we need to forward model everything and then bring that to the observational plane, and I think make a contact. I think we're ready to do that. I think that there's a lot of number of efforts that's going on that trying to forward model observations, and then and not only do that in XZ, but also do this in multi-wavelengths. So maybe we're moving in the direction of coming up with a sort of coherent modeling program for the multi-wavelengths astronomical survey. I think that maybe that's another area that we can probably push on in addition to sort of computational frontier. Just my 2 cents.
Yeah, one of the problem in this game is to keep our knowledge throughout all the redshift range we have. So one thing is to understand, to make this kind of work at low redshift for low redshift simulation. But then with data, you will have high redshift clusters that are the one that we don't know. And there things will get really tough. But yeah, we have to start. So let's start from redshift 0. So I guess we move naturally to the next slide. So Gus, if you want to.
Yeah, Daisuke, you touched on several aspects that are here on this slide. So one is to try to be sort of globally aware of all of the relevant simulations have value for your science, and to try to incorporate the full spectrum of expectations from those simulations. That's hard. I mean, Dhayaa's presentation was looking at one specific property that required only the exchange of very relatively small data sets. But to look at more sophisticated things like properties derived from imaging, properties derived from spectroscopy, to actually make synthetic observations requires a much deeper level of access into the hydrosim data. And so maybe we could first address the benefits question to multi-sim studies, and then work on the question of where's the infrastructure to support this, and how do we build out better infrastructure to support essentially the generation and analysis of multi-wavelength skies for cluster science.
I don't know if anyone has. Yeah, go. So sorry, I cannot see the screen and the.
I think
people.
Mila had raised a hand. Yeah.
No?
Yeah. Hi. So, I love multi-simulation studies. There's a few ways we can go about this. Right. On the one hand, we can benefit from the trade-off of large simulations with lower resolution but better statistics, and then smaller box simulations with higher resolution and possibly incorporating more physics. And so any projects that can sort of combine those two strengths would extract a lot more information from the many simulations that we already have lying around. It does. In my experience, I've come across two barriers. One is that there are so many simulations in the world, but many of them are difficult to access unless you are, you have a full-blown collaboration with a certain team. And often it's not transparent how to do that. So there's simply the question of how can a person access the simulations that exist. That is part one. And part two is I'm always surprised by how little funding is allocated to theoretical and archival studies. I was I'm fairly young. I just started my postdoc, but I got to facilitate a panel, like a grant proposal panel earlier this year, and it really broke my heart. There were like $70,000 allocated for archival projects, and I was like, that would barely fund one person. So if we're not funding people to do this, then how can they do it? Yeah, those seem like two of the bigger challenges.
You are wise beyond your years, I will say. Just a comment, and I apologize, I think my video is freezing and I'm continuously turning it off and on. But I would say that the key difficulty is that we're working in an international setting with international collaborations, but funding is typically a national entity, right? And so what needs to happen, I think, is that just the same way that ESA and NASA talk to each other about billion-dollar projects to launch into space or build on the ground, you know, they need to be talking to each other about cyber infrastructure is the term we use here, or e-science infrastructure is the European term, and to build out common shared environments, particularly oriented toward data storage, with analysis built into the infrastructure. And I'm thinking here of Alex Allais at Hopkins, for example, and his Datascope idea, which is a multi-science sort of facility that provides that kind of support. But it's hard because it's a question of, there's ownership questions when people spend a lot of time putting together a big simulation like the TNG collaboration. They want to exploit it first, and then make it public. And then there's the question of how do you afford that trade-off in terms of in the handoff of the data and the rights to access the data as the things progress. So just some thoughts there in reaction to your comment. And Daisuke, you have your hand up.
Yes, I think Mila, I think you're astute in recognizing these funding issues, which is real. There are actually some funding. But first of all, the funding for modeling and theoretical computational work is minimal. That needs to go up. But beyond that, I think there are some funding for example, specific mission. Like if you go to NASA, there are actually funding for things like Roman, or if you go to DOE, I mean, the Rubin has its own sort of funding from DOE and SF, but they are all survey-specific funding. This is not helping because we're actually developing simulation that could be shared with other surveys, but everybody has its own in-house computational resources that's specific for their mission, and they're not sharing. I think what needs to happen in the funding landscape is to try to actually start really think about multi-wavelengths astronomical surveys and what's needed for theoretical effort. So I think the funding structure for cross-survey analysis, doing computational modeling, and I think there's a recognition that combining multiple probes, like cluster, for example, with clustering of galaxies, or BAO, maybe clustering of galaxies is closer because it's both nonlinear objects. And there's quite a bit of effort going on within various collaboration, but we rarely share the tools together. So I think that in the future, I think we should be advocating for the sort of cross-survey type analysis and how to develop infrastructure for that. Yes, I think that has to happen at the funding level. But even before we get there, I think that those of us who work on things like Rubin or LSST, Euclid, I think this is an international effort. So I think we can actually work together, and actually share our data sets. And I think, as Michelle said, I think we're not here to monetize all of our data. Sharing our data actually only helps the community. So I think we should be more collaborative. And I think that before the funding infrastructure really come and sets in to make everything ideal, which might take some time, I think we can still do the grass efforts within the community and actively talk about sharing data, collaborating, and actually identifying projects that are shared among various different groups, and maybe really start to work together.
Yeah.
Any other comments on this issue? Some folks want to?
So I did want to bring back the discussion to the point, I think it was you who made the point that, right, if you're sharing just data products like a merger tree or things that can be tabulated, it's far easier for simulations to do that than it is to share raw data. And I think there's certainly an aspect of infrastructure that needs to be developed that enables, well, I think part of it's, right, like how easy can you access computers at another institution, right? Or something that's like owned by the DO or funded by like the DOE or NSF if it is international. So I think there's also like an access, and in addition to access, like it would be good to have like easy to use instructions. But that's also person power, which requires funding. So I kind of wanted to highlight those additional like components to the barriers already stated, that it's both access and ease of use to actually make that happen in addition to the funding. Yeah.
Yeah, and then we have to get ready. So suppose that we are in an ideal world where we can share everything, then we can actually compare what we are sharing. So we have to define a protocol to really make things talk one to each other, because I mean, today maybe this is not exactly the case. It's very difficult. You always have to pay attention when you are comparing simulation one among the other, and especially when you are comparing, of course, simulation with data, because everyone gives for granted some definitions and some things. But so at least from our side, we have to be ready. And I think.
Shall we move to the next slide?
Or yeah, okay.
Here's a provocative question. Should we hit pause on cosmological analysis, canonical S8, sigma 8 omega M plane? I don't know if any of the SBT Act folks are on right now, but I know. I mean, it's Tim. You guys are working hard, and it's not that I'm not suggesting that we stop. I think the question is more: are we really trusting the underlying population model, and can we really verify that that model is correct? And I guess that takes us to the third bullet there of the end-to-end survey likelihood methods applied to synthetic surveys. There's a lot to unpack here, but I apologize.
Maybe I maybe share a few words about this. I think we should not put pause on this, is my personal opinion. And the reason is that I think we've learned, and I think the field was stimulated by, for example, the Planck CMB cluster tension, which came up back in 2015, and the fact that sigma 8 didn't agree helped us really scrutinize and look into our own simulations and analysis pipeline to see what went wrong. So I think it was inspired by, motivated by actually seeking this fundamental cosmology parameters, and there was tension and hasn't, somewhat mitigated, but along the way, I think we've learned a lot. So I feel that from that past experience, these cosmological tension, once it's refined and error bar shrunk, I think we will identify some tension that needs explaining, whether it's astrophysical or possibly even some, hit the jackpot and actually it's a cosmological signal. Either way, I think it would be a progress. So I think that the continuing to search for, these lofty goals of cosmological parameters, I think is actually a healthy sort of endeavor, and which will, that will push us to actually, do this better.
Maybe to help us to connect with the other cosmological probes. I mean, it's the most direct way that we have to talk with the other cosmological probes. Otherwise, we will learn other things on cosmology, but we will end up in comparing clusters in different wavelengths with different surveys, but not with other completely different informations. But Tim?
Yeah, I also strongly vote that we do not stop this. I mean, maybe I'm biased, but I do think that there is a lot of promise, and we can improve this, I think, a lot. What's important that people really think about all the systematic things, which all the sources of systematic errors which can come in and properly marginalize over the uncertainties. And I mean, I would argue that we're trying to do this. At the moment, we are on the SPT side. I think the limiting factor in our view is really the precision of the mass calibration at the moment. And I would personally expect that, for example, once the DS lensing is completely incorporated, that will shrink quite a bit. And then you will start to get more to the systematics dominated regime, where both lensing systematics and uncertainties on the selection modeling and the mass modeling, they all play a role. But if you investigate how big you think realistically they are at the moment, you can account for this, and then you see which things are the most important ones to improve on. I mean, on the other hand, I'm also a big fan of the multi-wavelength analysis, because they can really help you to do more consistencies of the analysis and especially test your selection function. That's to me the biggest thing. I'm wondering how well you control this in the future, the selection, more than the accuracy of the mass measurements. That's, I think, a smaller problem, in my view, at least.
Thanks, Tim. I do agree that the eyes on the prize of really focusing on cosmological applications helps drive a lot of the astrophysics understanding, right? Because that's the part of the virtuous circle. Johan?
Yes, so I also do not want to stop this quest for cosmological parameters. And I agree that forward models are the key here. The main difficulty I see there is to model properly things we don't detect. So if you want to have a proper estimate on the uncertainty on your selection function, you need to be able to understand things you haven't detected for if you want to go to the group regime for your mass function experiment. And so that you are, let's say, X-ray detecting or optically detecting. It's a key thing to be able to simulate properly things you detect using data, but also things you don't detect using different observations from different surveys. And it's not the simplest thing to do to say, yeah, that many things I should not have detected, but they're there, and that's my incompleteness.
Yeah, it's a very good point, Johan. And it becomes even more complicated if the scatter in your observable runs with mass, right?
Right, yeah. Yes.
Tim, you wanted to
a comment to this. The things we don't detect, that is indeed a concern. I think at least at low redshift, we will be able to check this well, right? Because you can do things like shear peak statistics, so basically lensing detected clusters, especially once we have the big stage 4 surveys. We know lensing is not really good in finding clusters because it really picks up the projections also. But I think that's something which you should be able to get pretty well from n-body simulations, actually. And if there is a population of basically clusters which you miss in your cluster survey at higher masses, that you would see it there in the shear peaks. I mean, this gets more and more difficult if you go to lower masses, but especially at the higher mass regime, I think we will be able to check this at lower redshifts at least.
Matteo?
Yeah, one thing, perhaps we could turn this question and we could ask ourselves, how far should we remain away from the limit of detections? So if we should well define the detection, the regime in which we are sure that what we should detect, we detect it. And therefore limit our observations to that. I mean, we lose power, but we are sure that we know what we are doing.
Yeah, but there are regimes in which you cannot do like that. I mean, you will end up at high rush having no objects, basically.
Yeah, exactly. With limiting, I'm not only thinking limiting mass, I'm also thinking limiting redshift.
Yeah, but a pity to limit ourselves in Rasia.
I know that, but it's also
really
a pity if we get something which is wrong.
Yeah, that's true. Yeah, maybe like in the last point, we could use some small, well-known sample to understand what we are looking for, and try to understand our incompleteness and our capability to model all the objects. So maybe like in a serendipitous way, we discover a cluster that it's not well behaved at high redshift. We study it very well, and we see if we can find it using our model. And so our models and our tools, and so we can try to use this kind of object to parameterize our capability.
We also have deep fields. I mean, there are the Euclid
exactly.
deep fields and other deep fields. I mean, these are going to be very precious on that.
I mean, yeah, that's exactly why we have deep fields in Sartre, yeah. But yeah, in this case, you will also have the multi-wave. I mean, if you have the small samples that you look in different that you study in different wavelength, then you will have additional information. So yeah, like follow-up observation of the deep field of one survey in another band, or this kind of thing.
Would anyone like to comment on that last point here, the small team research? We've 45 people on the call. I don't think many of us are members of large collaborations, but not all. Any thoughts on making sure that as big survey analysis is done, it's also aware of some of the detailed measurements that are available for some of the clusters in those big samples?
Can you elaborate on the flavor of the question a bit? Are you thinking in terms of just making sure these happen, or funding, or?
Well, yeah, that's a good point, Anthony. I guess I was thinking more on the analysis side, like essentially, if we would get in a paper with Arya Farahi a few years ago, looking at the locus clusters, that there's a likelihood method where the true mass of every cluster is part of the is one of the degrees of freedom, and you get posterior estimates for that true mass. And so I'm imagining a likelihood framework like that, where your measurements, for example, of splashback radii could possibly be brought in to place some priors on particular clusters that were part of a larger sample. And it's not something that we're really doing at this point in time, but I'm thinking about, 10, 20 years from now, where there's a whole bunch of stuff out there in the literature that you could potentially scrape and employ as priors.
Yeah, I guess there are two ways that one can try to go about that. One is like designating some canonical sample for basically an observational version of a challenge. And the second is trying to do something more like the joint constraints with machine learning and integrate it from a larger ensemble. I think there's a role for both personally.
Mm-hmm.
In terms of how to set that up and inspire that, that's a separate question. I'm not sure I have a good answer to, other than having it organically evolve.
Yeah, but I mean, we already like with many of the people that are here, we work on this Clash collaboration, so Clash VLT, and so we compare. I mean, we really take a very small sample of clusters and analyze them very well, and then from that sample you can put constraint on simulations. I mean, constraints on your understanding on simulation. So you really reach the level in which your simulation have to answer to your questions. So you understand. I mean, and then you can use this knowledge on your simulation to I mean, to further explore astrophysics and cosmology with clusters. So for me, that's an important way to I mean, yeah, way to proceed to go.
Should we maybe jump to the next slide? There's just a couple more left, I think.
Yep.
And this is a slide that I selfishly put a plot on from the 2002 Hubble volume paper. But just a few exercises that I would love to sort of stimulate in the community. You know, Michelle's the whole session on machine learning. I think there's a lot of potential for using machine learning for classification. That is to say, I'm thinking here about both optical and SZ, where the observed signal is you know, projected version of the true intrinsic halo signal. And so I could imagine ML being useful for classifying clean versus complex halo sightlines. Also dynamical state. Also, and I just edited this slide, so I'm not sure why the last edit isn't coming up, but I had orientation after dynamical state and 3 dots, you know, basically, you know, your favorite property here. So that's one exercise. And then another exercise that it's getting close to being ready to do for between optical and SZ, and with eROSITA, it will soon be available with X-ray as well, is to start looking at this sky surface density mass scale, characteristic mass scale, meaning this plot that's down here is, God forbid, figure 16 in the Hubble volume paper, but I thought one of the more interesting plots in the end of the day after 20 years. And what it's showing you is in narrow 0.1 redshift bins, it's showing you the rank ordered halo mass and effective temperature in the bottom panel. At the labels for these lines are the number per square degree per unit redshift. So 1,000 per square degree per, sorry, 1 per 1,000 square degrees per unit redshift is the top, the very rarest systems. And then you get more and more common as you go down. And, you know, I think what would be interesting is if you really are complete above some, if you think you're complete above some mass scale in either X-ray, SE, optical, you should be hitting the same characteristic mass, sky surface density mass scale, and tests of that would be, I think, interesting to address systematics and understanding of essentially the scaling relations that are put into these cosmological analysis. So I'll just be quiet now and see if there's reactions, and maybe some of this is being done, and I'd love to hear about it.
I mean, I'm just going to echo what you said, Gus. I think it would be really, really interesting for the ML for classification of dynamical state in particular for me. What, following from Michelle's talk yesterday, what the models pick out as being the most discriminative feature between dynamical state. That would be really interesting. Somebody's working on that.
Thanks, Lindsay. Any other thoughts, reactions?
Gus, on the plot you show here, I'm not sure I understand why. What do you mean by sky surface density mass scale? What is the difference then with the halo mass function, the usual stuff we are doing?
Yeah, this is just the halo mass function integrated up in volume and then rank ordered in redshift shells. So it is the same thing, yes. I guess what I'm inviting a consistency check across surveys that if you really think you're complete above 510 to the 14 solar masses between redshifts, say 0.2 and 0.5, then you should be reaching the same sky surface density in that redshift range as another survey that claims to be complete in that mass range. It's a pretty simple exercise, but I think it's an exercise it's kind of just an abundance matching exercise, but across different selection methods to demonstrate consistency in the finding of halos. Does that make sense?
Yes, yes. Thank you.
Daisuke?
Yes, maybe regarding this role of machine learning in cluster cosmology, I think I have sort of two different ways of thinking about this. First, when I hear things like machine learning classification for different types of clusters, I guess the question is, why do we want to classify? And after doing the classification of relaxed, unrelaxed clusters, what are we going to do with them? So I think the answer to that question is whether we want to do that or not. And I think it's good to classify, but I think the question is, what do we want to do with them? When I thought about that question, one of the things that we actually did, and this is a paper by Green et al. 2019 with Michel Numaka, is that we asked a slightly different question. We actually are interested in cluster masses. So then can we use those information in X-ray data to actually improve cluster masses by using machine learning? So here we decided to focus on cluster masses because I think that maybe that's actually important. And then actually train the machine learning. I mean, you actually use this additional information, like morphological information in particular, to see if that like information that's often not utilized, does that help improve our cluster mass estimate? And I think machine learning is very good at like exploiting that kind of feature. When we provide this additional information, it certainly did learn how to actually improve the masses, and we tested this in simulation. So that was a slightly different, instead of actually using machine learning to classify object, we just let machine learning to figure out how to optimize the sort of the target observable that we are most interested in. So maybe that's slightly different take on how we end up actually using machine learning for this for cluster cosmology effort.
I mean, I think with dynamical state, I think the reason why it would be really interesting is because, well, several reasons that it's interesting to know dynamical state away from like just the mass thing, but in terms of galaxy evolution, infalling subgroups, how at a given redshift, what proportion of clusters are super messy or aren't, like just those sorts of questions will be really interesting. And at least in terms of galaxy dynamics, we have, you know, these typical ways to identify substructures in phase space that are like, you know, 40, 50 years old. So it would just be really interesting to see if an ML model would pick out something that we didn't notice in terms of like, what is it focusing on that makes, what is the most important thing for that classification? What is the most important feature of the data? I mean, it might be something that we already know, but it might also be something different. So I think that would be what would be interesting to that, aside from sort of the cluster cosmology part.
Just a comment, Daisuke, on your thoughts about what we would do. One thing that we could do if one had the ability to separate out clean sight lines from dirtier ones is that the clean sight lines are more likely to be following the canonical power law plus log normal scatter in the observable mass relation. And so I think you
I don't know if you hear him. I don't.
No, it's frozen.
I think he dropped out temporarily, might have frozen.
Okay. Gus?
He's back, I think.
Yeah, you're
okay,
back.
am I back? Sorry, I'm sitting in my office at the University of Michigan, and the internet, the wireless is still crappy. I don't understand. So I was just going to make the point that the clean sight lines will give you more regular view of the halo population, and that projections typically add some skew into the mass observable relation, and you'd be removing that skew and making it look more log normal, I think. So that's the point I was making. And unfortunately, I have to teach in 1 minute, so I'm going to have to disappear. But thank you all, and I'll leave you in the good hands Barbara and Camille for closing out.
Thanks, Gus.
Oh.
Thanks, Gus.
Bye.
Thanks, Gus.
So we can, we actually have 2 slides that could take like 3 hours to discuss or 1 minute. So we just put together the question that we had when we started this this conference, and so we see if we have something to say on it, or otherwise we can just conclude here our discussion as the organizer, the main organizer decide. I don't know if because I cannot, I'm afraid that if I unshare the screen to see the clock, so I don't know what time is it. So
it is time to end. I mean, if
so perfect, we have the thank you slide. We have we are ready to all the options. So we really want to thank the local organizers, because it was tough to organize this conference for the previous year, then move to this year, then remotely, then maybe in person, and so I think they did a great job.
Let me say that Lindsay was a driving force to coordinate all of us. She was.
And I want to say Bruno did a lot of, was extremely helpful as well. So, but I also want to say thank you to everyone who contributed, because I mean, conferences take a lot of work, even virtual ones. And I think everyone presenting a poster, giving a talk, the SOC, reading all the abstracts, putting the program together, chairing discussions, it's a lot of work for a lot of people. But I think, I think when we sort of proposed this meeting a couple of years ago, the goal was to, hear from all corners of cluster cosmology, multi-wavelength simulations, new machine learning models, methods. That was the goal. And I think despite lots of hiccups, I think it's come together nicely. So yeah, thank you to everyone for contributing.
Yeah, also we have a lot of discussion from I mean, we managed to really discuss and talk to each other. So I think that was the most difficult things. And it seems to me that in some way we managed to do it. So also thanks to all the participants that come and talk with us.
Especially across different time zones. I forgot to.
Yeah. Yeah.
Giving talks at midnight. So yeah, thank you for that. And maybe in a couple of years, there'll be an occasional in-person meeting. And,
yeah, let's hope.
Who knows?
Yeah, fingers crossed.
Yes, at some point.
Okay.
So,
great.
Thank you.
Thank you.
All the presentations have been recorded, so they are online immediately, and I will collect the presentation and themselves and post them on the website in the next days.
So the discussions were not recorded, right, Bruno?
No. The discussion will not be recorded, will not be put on YouTube. I will cut that. Today I let YouTube running, but I will edit out the discussion. And the past days they were not recorded.
Okay. It's too bad in a way. It's good to have the discussions. In the old days, we had proceedings and we had the discussions in the proceedings after the talks. And those are the most fascinating parts of when you look at these old books. The most interesting stuff is the discussion with these big names, arguing about things. It was just remarkable.
Yeah, saying that omega matter was one.
I've made progress.
It's not one.
You didn't pay enough attention, Laura.
Sorry. This is a very surprising result. That's the result of this conference. Thank you very much, in particular Lindsay and Bruno. You've been great, and also even Anna Maria, Riccardo. Thank you very much.
Let me add my thanks too. Thank you.
Ciao.
Ciao.
Right.
Well done, Lindsay, Bruno.
Thanks.
Thank you very much, everybody.
See you next time.
Take care.